Sorry. Sorry about that. So I was saying that we have 24 people online, around 8 here in person. So everybody can request GPU machines if you want to explore and do things faster, because well, the kind of things that we will be doing today are very practical, are just the pragmatic way of working with these frameworks. And at some point, I will show you one example where I will be submitting a job to the cluster. So the way you do this for real research, not just for learning, for real tasks, which will be a little bit more complex for some of you if you are not familiar with the command line interface. So you can skip that part. I'm sorry, this will not be an introduction to HPC by any means. So for those who can follow Unix, Linux, and submissions on an HPC cluster, that they can take advantage of this, or just watch and see that in the future there eventually you can do things at large scale efficiently. So let's start by this. Go and copy the data. I add a few files to the repository, to the system. So what you can do is execute this command. Oh yes, yes. Sorry, I think it's preset 4 for that. Yep. Good. Yeah. Okay. So, and I will be doing this slightly bigger, so everybody can see this. I will put it on the top. So this is why share tutorials deep learning, and you can copy that to your, let's say if you have this crash sim link, something like this. No matter where you are, you can execute this command. By the way, you reach this terminal from here, you go to open on demand, you click here in clusters. So you will be like open a virtual terminal on a tab on the browser that survives for a couple of minutes. So it give you the ability to do a few things. So this is the command that you can execute. If you just want to remove everything that you probably edit or introduce, that you could be a little bit more aggressive, and that will not only copy all that data, but delete what is not present on the deep learning folder. But you need to be careful. If you don't put these things correctly, it could end up deleting your own data, something that is outside. So you need to be careful with when you use this type of command. So if you want to be safe, this will just copy the new notebook that I add, some scripts that I had yesterday. So that's it. So for today, we will have a very packed session. And I will start with presenting in practice how the different frameworks, the 3 main frameworks for deep learning, how they work. In this one, creating a new one, and I don't remember which one I will present first. So let me see. Where to go? Scratch. Okay, so I will start with TensorFlow. That's the start. After that, I will show another example with PyTorch. After that, MXNet. I will skip 6D. Those are advanced topics. I will not be able to cover those. And instead of that, I will be covering this new notebook, MXNet, training C410. So this is, and I'm not sure if I will have time to cover some of those notebooks, and eventually we'll mention and execute something for recurring neural networks. So let's go here, select Singularity, and select Community GPU Inter. That will be the queue that offers us GPUs. 4 hours is okay. CPU cores, or you can request 8. 1 GPU card. I will be using TensorFlow TF2. It's the second one, not the first one, the second one. And click launch. So I will be paying attention to the chat too, just in case.
Can you just go back a little?
Yes, I will recapitulate this. So okay, Nate copied on the chat the command. That's okay. And Patrick did it too. So thank you very much. So let's recapitulate. So let me see. What I did was, okay, you will land on this dashboard. You click here or you click here, Jupyter Notebook, and I select Python via Singularity. So that will use one of the Singularity image. So I mentioned this probably the first day. Those are containers like Dockers. So it's one file that contains the file system of an entire Linux machine. On the most part of a Linux machine, and will allow you to execute code if you were running on a different, potentially a different distribution of Linux. And those images that we have here at the bottom I will show you, and those are images created by or provided by NVIDIA, optimized for their GPUs. So community GPU Inter. So we have a bunch of queues here. So we usually use standby, fairly common, no GPUs here, 4 hours, that's the limit. And we have a few those that start with com, that mean community. So everybody can use, because everybody can request an account with us for free, not cost associated to that. So after you get your account, if you are a student, you need a PI, you need an abstract, like the kind of research that you plan to do. But after you get that, you can execute in all those community queues. We have some with a small amount of memory. Again, our definition of a small amount of memory is 90 gigabytes of RAM on a machine. Our definition of medium is 180 gigabytes. Large, we don't have large here. We have an extra large that is 760 something gigabytes of RAM. And of the other parameter is the time, the dwell time, the amount of time that you can run a job continuously on the machine. This is for a week. This queue is for a day, week, day. So you select what you want. And sometimes you need more than that. So you have basically two choices. So either you buy machines with us, and we put those, or the PI, your PI will put those, we will put them on under a name, as under a queue that belongs to that researcher, so they can use it. And he can use it, and he or she can use it in his or her students. So that's one option. Or you start using, for example, for long deep learning trainings, checkpointing. So you say that your best model, and the next time you reload, you recover your wakes, and you continue for another week if you want. So those are the options that are available. And so those other queues that you see here are queues that belong to one particular researcher who both nodes with us. So we have those available for that. Wall time 4 hours, number of CPU cores. So I would say 8 if you are requesting this with GPUs. The first share is 8 cores per per GPU. We have 24 cores in one machine, and we have 3 GPUs. So it's 1 GPU per core, is 8 CPUs per core per GPU card. So I will be requesting just one GPU card. So that will give us pretty much 1 GPU for everybody. Will be fine for the exercise. And Jupyter, and the other selection here is selecting the second option here, NGC underscore TensorFlow. This is 2022 and July, and then this is the latest version of this of those images. And after that, you just click launch.
So we can actually connect also on Jupyter Lab as well.
No, those are, what do you mean?
Jupyter Lab.
Yes, you can select Jupyter Lab. I think I installed Jupyter Lab. For sure, is this in the C Python, the Jupyter Labs. I installed that, the latest version of Jupyter Lab. If you want to use it. I'm not so sure about those NGC images for the specific frameworks, because they come almost vanilla for me. So that I built from the Docker recipe the Singularity, and I add a few things like networks, scikit-learn, the watermark. So a few extra packages that I use for these notebooks, but I'm not really sure about Jupyter Lab. So you can try. If it fails, because Jupyter Lab was not installed on those. They only have the older Jupyter, the traditional Jupyter, not the Jupyter Lab. But for the C Python versions, yes, you can go. I know for sure that they are there. So you click here, connect to Jupyter, and you get into this. So I will be deleting this because I will be generating something like that in a minute. And you click here in Scratch, you go to your deep learning folder after you update it. So, but this time the connection has been lost, security. So you execute this command, you now have new notebooks, and at some point you will notice where they are, notebooks. So we will be going into chapter 6a. So a little bit how TensorFlow with Keras works, the different ways of creating neural networks. Up to this point, we have created those networks in a very simple way. And I will show you some other alternatives, more elaborated for more complex architecture.
Excuse me.
So I will be launching that.
Could you please, can you hear me?
Okay, well, I can tell you right away where you can find the documentation for Globus. It's right here. Someone was asking about. So if you go here, and I think it's basic users, Globus Online. So here they have like, I think a video or a guide on how you install your endpoint on your computer, Linux, Windows, Mac. You install an endpoint, and when you install Globus, you click here, you get you get a tab open on your browser, and that way you can transfer data between your computer and the cluster. And so that's the solution that you can use, for example, to take all this data. If you take all this deep_learning folder, everything is there. So the notebook should work if you have the packages. All the training data is in the data folder. The images for the notebooks are in the images folder. So everything is pretty much organized there. So this is one option. If you want to see, probably will not have time to go into the details on installing that, but this is where you can find it. So I will be executing this. And I'm not really sure if I probably can keep this data for 1 week, maybe 2 weeks, but at some point I need to remove that data because I'm not sure about the possibility to distribute the part of the data there. I'm not sure about it. if you can redistribute that. You can download it from the original sites, but I'm not sure if you are allowed to redistribute that. So I probably will, in 1 week, I will remove the whole folder. So this is what I'm doing. I will be loading here TensorFlow, and I will be loading Keras. So it would put this Keras in what is called, well, the namespace for using Keras directly. What else? I don't remember why I just cycling. Maybe I will be doing something particular there with that. So what the important part here is I will be importing this. Of course, I will be importing NumPy. And this is pretty much boilerplate for me for be able to plot when I need in the notebook. And this is one thing. When you are running on the cluster, this is particular for us. On the cluster, we don't have internet access on the compute nodes. So when you execute the examples that you find over internet, and there are many tutorials over internet, and so how you use TensorFlow, how you use Keras, how you use PyTorch. One of the things that you see is things like this. So you gather the data with something called like Keras dataset, CFAR, low data. That will not work in our cluster because we don't have internet access on the machine. So you need to download the data in advance always. And so that's why I changed, and I was here showing you how you can download some of the traditional well-known data sets that I use for learning, deep learning, for making some cases for publications for the people who work on computer science in this area. They present the paper or the results based on CFAR 10, CFAR 100 to prove as a proof of concept. And so Keras offers the ability to download a set of those pretty well-known, pre-made, pre-organized, clean, and everything data sets. And okay, that's the reason with scikit-learn, just to mention that as a side note, there is an equivalent way for doing another set of data sets for scikit-learn. So they have that. We cannot use it, so I have to tweak the notebooks or the sources for those notebooks to adjust for that. So I have to download the data in advance. So that another thing is that we have an issue with the SSL on the machine, so I need to deactivate the verification for SSL. Otherwise, many of those things just, if you execute it from the end node, even with that, it will not work. So here I will be working for this first example with another very traditional data set that is called the fashion MNIST. Is very much a drop-in replacement of the MNIST data set. By that, I mean it's exactly the same number of images. They have exactly the same size. They are 28 times 28. They are grayscale. They have 10 categories, but instead of the 10 digits, what they have is like shoes, chairs, coats, so different well, things like that. We will see in a minute. So this one is another solution. It's a little bit trickier than MNIST, but it's still too simple for today's standards. So that's probably the reason why people publish with that, because even with very bad ideas, they work. So they succeed publishing, but yes, typically people move into CFAR or CFAR 100, CFAR 10 or CFAR 100 to make some claims on a better performance or better analysis or something on the data. But I will just change the MNIST into this one. What I'm doing here is just replacing what the code is doing behind. So I have the data in one particular place in one folder app. I was explaining this to you before. One folder app the folded data, inside that the folded keras, inside that the folded data set, inside that the folded fashion minutes, and I have there 4 files compressed. The training set and 10,000 images and labels for the test. And so I am recreating the function. I basically, recreating the function that will allow me to, instead of using this, that will require me internet, I will be using this. That looks the same, but now I can get the data. I can check with the shape of those tensors that they are actually 60,000, 10,000, 28 times 28, and they are at this point they are integers, unsigned integers with 8 bits. So as usual, same thing that we always do with those grayscale images is that we are divided by well, I'm doing that. Oh yeah, they will probably do the conversion. That the conversion automatic. So divided by 255, I'm getting exactly the same, and also separating in a small section here for validation. And so that's why I'm taking from those 60,000, I am taking a small portion of that, 5,000 of those for validation. And so I will be showing you how they look. This is one of those cases, and they have like an array here where they say what they are, and those are the classes. So we have 10 classes there, and this one in particular. So the first element, which was the image, the class associated to that is code. And this is what we are doing here, taking the shape. So everything is fine at this point. And here I am showing you a grid of those, so many of those. So I'm taking, I think, the first, well, a certain number, just to show you with the title, which is the class associated to it. So from far away, you can pretty much get an idea what they are, how they look like. And this is, well, the first thing is this will already solve this way of building neural networks, is just a sequential. This is really nice, really simple to build a network that works like this, like a straight sequence of layers. Moving forward. So here I'm saying that I will be creating this is one way. So explicitly you create a model and you say the model is an instance of the sequential class, and you start adding to a list different layers. So objects of the class or a subclass of layers. So the first thing that we'll be doing here is flattening the array, flattening the 28 and 28. So we're getting the array and adding a dense layer of 300 here with a ReLU for activation. You see here another dense layer with a ReLU. Let's see if I can stretch this and you get a little bit bigger. So for those of you who can see that. ReLU, and finally a temp. So we are pretty much following the same prescription for the digits. Now this time, so now we have the opportunity to enter in more detail on the practicalities of this. So flatten, of course, is taking an array, is taking a rank through the tensor that you are receiving, and you're just stretching that. So reshaping those tensors. The dense, so 300 neurons there, and that will be fully connected to the inputs in this case, and those 100 that will be fully connected to the 300 from behind, and at the end, then another 10 with a different activation function which is the typical function that you use for classification purposes. And we explained before why, because this function will give you 10 numbers. When we add them, they sum 1, so we interpret those as the probabilities for being one of those classes. So same thing here. So we saw this a lot. Oh, well, I forgot to do something here. Oh yeah, forgot to execute this box. And yeah, so this box. So this box will open here a box. So you probably will see something slightly different here. So I am getting the older generation. I have no control on that. Well, not directly the way I did it. So I'm getting a big 6,000. Probably some of you will get a better version of this card. It's called RTX 6000, which is kind of like 2 or 3 years old. And by the way, one of the reasons we are offering this workshop is because probably around by the end of the year, maybe beginning of the next year, we will be getting a new cluster, GPU base. It's a cluster of around $1 million that we got from NSF. So that cluster will be fully GPUs. So compared with this one, that we just have a small portion of machines with GPUs. So the main use cases for GPUs, at least in our community at WVU, are those using this for deep learning and those using GPUs for molecular dynamics, for classical molecular dynamics. And some other cases around would use this for related tasks that are, let's say, close with a strong emphasis on dense linear algebra or in general linear algebra that fit the purpose of GPUs very well. And so that's the message here. So we will be using the GPU. We know that the GPU was found. They have 24 gigabytes of GPU memory available to us. So it's right here. So it will give us some information that we are on the right path with this. So the training will be fast. So this is the sequence, the summary of the model. We saw this already. Notice that this time I was using bigger networks. So the number of parameters is not 55,000 as we did before. Now it's 260,000, but pretty much it's the same. This is something that we use in Keras when we need to clean the session, so then the networks will start with so clean some clerical data that Keras store when you execute this over and over. But this time, another thing that I'm doing here is for the purpose of reproducibility of this, I am cleaning or initializing or forcing the seeds for the pseudo random number generator. So I just put in a number. So the function that generates those pseudo random numbers will give me the same numbers every single time. So I will be predictable when I'm doing. So here you see, and one model, why create a model? And this, by the way, this is another way of doing things that so you saw before, and this was actually the way we used it the first time for the MNIST, the original MNIST, the digits, that was putting actually a list of layers to the sequential model to build it. This is another way, it's just a variation of the first one, and now we have a few properties of a model. One of those properties are the layers. So you see here what they are, so you can check on them. And actually you can see, for example, they work also like this. So you can see which is the first layer, so you can inspect layer by layer. And in some other and more advanced things that we can do, probably we don't have time, that probably is an advanced thing in that was notebook, is that you can inspect how the different kernels looks like by creating a special model that has multiple outputs, so you can see the kernels or the maps, what they are producing to us. But that's kind of advanced, so I will not be covering that. So same thing, same model, same number of parameters, nothing have changed. So this is a nice utility that Keras offered to us. If we install a package that I put on the top of this, so for beginners, this is handy. If you install this package PyDot, you will be able to see a graph, a graph of the network. For this, is kind of silly because you can interpret that. Oh, I forgot to install it on the. Oh no, I have it. I forgot to install graphics. Great. So it's in the C Python, but not in the node. Otherwise, what you see is like a graph, boxes. This layer go to this layer, go to this layer. We'll be probably putting something like this just to give you an idea. This will light. Okay. It will be making something like this. If you are executing this with the C Python, you will see one layer, the flat end here connected to the first dance, and after connected to the second dance, and after connected to the output. So for this one, it's super simple. But after, for some more complex networks, this opens like a tree. So you can go and select one portion, go into this one, which connect to a set of convolutions, and this one will put another set of convolution. You jump, you can have residuals, so you have like mappings that go to with the identity. We will not be covering those more advanced stuff.
They can't see that online.
They cannot see all this online because I was not sharing this thing. Right. Let me see.
I think you just need to turn on video for that one.
Yeah, no, I think it's, well, with some ugly thing. Well, it's not so visible. Well, not sure. Well, it will show a plot of a graph of the connectivity of those. Maybe I can show you that later if I execute this with the other C Python. So my mistake was this. I have PyDot, so I was thinking that was okay. But I also need a package that is called graphics that I don't have on those images. So you can also inspect the different layers. I show you with one briefly before, and also you can change the name, so you can name the layers if you want to get an idea. You can use them those layers as keys for a kind of dictionary for the layers, so you start getting more control on the architectures. And also, once you train those things, you can inspect the weights. So right now, what you get is whatever the garbage in memory was there at that moment, because we have not trained this network at all. So it will just pick from the memory. We have here the shape for the weights. So you can start inspecting one by one the different components of this. And the biases is a bunch of zeros. So I just put in the max just to prove you that there is nothing there beyond just zeros. And now we did this before, but now we will complete this a little bit better. Is the compilation. At least you put those three elements: the losses, the optimizer. There are several, SGD, which is the sparse gradient descent. This is one classical optimizer. There is another called Adam. Different optimizers just give you better or faster optimization. And you have to test a little bit. This is more like an heuristic thing rather than a hard science. So what I'm doing here, you can do this with the words, or you can just put the name of classes or instances of a class instance. So here I am instantiating an object from the SGD class. And by the way, those have more parameters. We will not go into little by little into those details, but you can control the learning rate. So how big is the jump? For some of those methods, the jumps are fixed. Some of those methods add momentum, and some of them, the learning rate, so the changes are adaptive. So when things are moving soft, they take more, they go more risky. Those are things that you can control here if you do it this way, with explicitly saying SGD and putting some parameters like learning rate. I think we have one example when we are doing this. So we have the model. I am here explaining this again. I already did it for the loss function for the cross entropy. We'll probably skip that, and here I make the reference for the documentation. So by the way, it's a good idea to always have the documentation at hand. You will see all the losses available. It's just not the categorical, it's just not the RMS. So there are more than that. Just keep your mind on that. So, for the optimizer, if you are happy with the defaults, you can just put the name like this, like a string. But if you want to have more control on that, you can actually instantiate an object of the SGD class. At that moment, you can select the learning rate, which is the jump. If you will be adding momentum, so this is like having a little bit of memory of the jumps that have been happening before, so you move in the future with more confidence or not. I don't remember exactly, Nestor, what they do. I need to double check with the documentation, the name, and some other parameters that will cascade into the classes that were inherited from this one. So that will be another thing. And some metrics. So one of them is the accuracy, which is good for this kind of problems, well balanced. So we are happy with that. And this is the important part. So this, sure.
So as we use optimizers for only the faster training purpose, or it also improve the accuracy of the model as well?
Let's see. The optimizer will be those things that will take the gradients and will improve over time those weights. So we'll give you, they will not, in principle, will not give you better weights. They will be giving you better weights faster. Faster. It's just that instead of taking 10 epochs to get it to a certain point in the accuracy, you just need 5. So that is the thing. So you will be going there. So if the learning rate is sufficiently small, because that's another thing, if the learning rate is too big, you will see on the plots, you will see some going up and down in the losses or in the accuracy, going up and down, because it will start jumping out of the range of the soft curve that is following on this n-dimensional surface. So if you notice that, you should reduce the learning rate. The penalty with the learning rate is a very tiny learning rate, and some people use a crazy small learning rate because they don't check it. And that's the difference when you do this like a science thing. So you control the parameters correctly, and you just throw that blind. Some people use 10 to minus 5 just because the previous PhD student who graduated last month told you that that was the number that he uses because the previous student told you that. And so that you should stop with that mindset and think, see, okay, let's start with a big one, see what it given me. See it, so I get a justification why I'm going slow, because a decent learning rate will help me to get the good accuracies faster. So it's not just 10 to minus 5 that will solve my problems. And by default, you see the default is what is the default thing? It's 0.01. So and some people, for some problems, they found that that is too big. So they start reducing, or they change the whole problem and they go into another optimizer that is adaptive. So those learning rates grow and shrink as needed. So in different points, they have other versions of that. So that's one thing. So let's continue. Metrics, and here the training. So this, I think this will be fast because I'm not asking for too many. So you will be able to execute this on your own. You will see here also something that we saw before. So the losses and the accuracy, and the losses, the loss function and the accuracy all on over the validation data. So you pay attention to this value and you pay attention to this value. That's the first thing that you do. You see how they change. You should notice that at some point, this one started getting behind, so it started getting not improving. Eventually, it could go up, down, up, down. So you see here 7, 7, 8. So it's still improving a little bit, but at some point you get that. So you get this one. Well, this one was not so bad. Eh? Pretty much got the same for the. Is this the network source? Then the trending source. Very simple. So we got 88% here, 88% there. So, and actually we got better on the validation, which is usually unusual. But that's not the point. The point here is presenting the machinery, no longer the neural network itself as a mathematical entity. Or it's just here is just the practicalities of this, how those things work in practice with a very particular framework. And so here I have the parameters that were used for the history. So I see the epochs, and for each epoch I can inspect the values, which was, and so history will contain all data that was produced for the during the term. So like a dictionary, and that is when that is why I'm using here. In this case, I was using pandas. For no particular reason. And here I am using here. So here I'm plotting the losses both for the training data and the validation data. And here I'm plotting the accuracy. Some people plot the accuracy, some people plot 1 minus the accuracy, so you get an error. So that allows you to plot this in semi-log, so it could give you put things in a different perspective. It's just ways of plotting this. So what else? Now, okay, after you get the model, so the real thing that you want is to evaluate that model with new data. So we have for that, for example, the test data. And that will tell us, okay, how good we are with this model. That's with some data that was researched. So with the model evaluate, we are just running the network with the data, and they will just give you the accuracy for that and the losses of that. So we got 86. So it's a little bit lower. And here we have more data. We have 10,000 compared with the validation data that was also not used during the training, and we got 88. So we are around this. So that is what I'm doing here. You can see here and what you get when you predict a certain number of cases or one. So I took 12 cases here. So it's okay. Make the predictions for then these 12 images that I will offer you, and they will return me here and rank two tensors or matrix where those are the different probabilities for the first image, the probabilities here for the second image, and they are hard to see this way. So what I did at some point was rounding the values. So where the values rounded, I can see very clearly that this one was this one was this one is winning. Here, this one was winning. Here was this one. So you see, there is a one that really shines, and the second one is significantly lower, one order of magnitude in this case compared with the first one. So after that, this is just practice with NumPy. I am taking, what I'm doing here is yes. Yes, probably yes. It's probably because I took this and I probably changed the epochs on the number of epochs. I did something, and I will at some point it was saying 10, and I changed it, and now maybe I changed the network. I put more neurons, so and I keep the text. So sorry about that. I probably introduced a change on the network, but I kept the text there. But what you see, don't believe the text, believe the plot. So for this plot, well, we can say still around 6, 7. So at this point here, let's say around 7, you see the losses are not improving. So you start overfitting, but still here, the validation was a little bit, yeah, here around. So at this point here, around 7 in this plot, you see it become flat. It became flat, the validation loss. It's not so evident here, so you can see it still. And the bad thing is that you still see here that this curve is under. So I did something with the network, so it will not be true. It will not be true. So forgive me about this statement that is confusing. Sorry. So let's continue. What I'm doing here is taking the predictions and taking the maximum argument here. So I'm taking here will be 9. This one will be number 2. So I'm taking that one. So that is the index of the correct answer, or the answer that well, not the correct answer, the answer that the network is giving to me. And that will be, I will be using that on top of the class names. So that you saw here the class names for this. And before here, where I have codes, shoes, tennis, where we have like where I have those. Yeah, right here. So those are the classes. So I am picking the number 9. So just making an indexing from those numbers. So this is just magic with NumPy. So I will be getting here that all those numbers, okay, all those numbers return this. So the first one was this one. The second one was a trouser. Third one was a pullover, desk, coat, sandal, shirt. So that was the identification from our list of classes. And so that is. Yeah, this is another way yeah, this is the way of, those are the classes, and this is the way of projecting those from the list of integers or the indices that we got. So that is what we did there. And let's see what I was doing here. So I'm showing you those 12, what they are. So at least as a human, you can easily inspect it. the image. From NumPy, we can see if the first array is equal to the second array, so we can check for equality in two arrays, in the content of two arrays, is returning true. And this is checking if all the values, so this one, MP, if all the values in this equality projection are true. So at least for this first set, it got it wrong. It was. And this one skips a little bit because this is a small example for something else. This is for regression, something that I never put too much emphasis in this workshop. So most of the examples were related to classification, just to keep like a coherent theme. But there are some other problems like regressions. In this case, I can mention a couple of things. Forget about what they are. I picked this for being lazy because this has not any science behind this. It's just house pricing. So forgive me about that. This is something that is appealing only for computer scientists. But, sorry about that. So what is different here? So I have just one dense layer, and the second layer just has one number fully connected to the third behind, because what we are doing is just predicting a single value. This is one thing. Another thing that you notice immediately for those cases when you are doing regression is that there is no activation function on top of the final layer. So we are not introducing any nonlinearity at the end. It's just the value, because that's what we want. We want that dense layer do the matrix multiplication. So which are the different values here? So those are like the size of the house, the number of bathrooms, the number of rooms, or the area, or to predict the house price. So just to show you slightly different values that you never saw. So different loss here. The SGD was okay. We already used that. 10 epochs, the validation, and the test. So we can offer all that to train, and you can get here the data that we see there. So my purpose was more to show you something that doesn't have a softmax at the end, so just to move you out of it. Okay. So now let's see to go into more. So this one is the first way in Keras to build networks. Now there is another way that is more flexible, that give you more chances of building a structure with more complexity, is the functional API. So we initialize this with zeros. So here, notice here. So here I'm declaring an input. Is again an object of the class, a subclass of layers. So I am saying here what is the shape, or the number of elements that I'm introducing here. I am declaring here the hidden layer connected here like an argument to the input layer that we put before. The second hidden layer is another object of the class dense, which the argument that it receives is the hidden layer that we put before. And after we are doing a concatenation of, what are we doing here? Of the input with the hidden, why are we doing that? Let's see that. Oh yeah, I am connecting here the input just to show you some ways we can connect some inputs with some outputs and new inputs even in layers, so we can skip from one to another. Let's say at some point you can go in here and use the output of this one and connect it down below by passing some layers, and that's something that is used in a very particular kind of neural networks called residual networks. So here is just playing with what you can do with that. So again, you cannot apply that. I will be training this.
Can you hear
So
me?
this one is the second way of creating networks on Keras, so with more flexibility. So at the very beginning, you always see those lists because the first dense neural networks, the first convolutional neural network that you see always offer this stack. But modern architectures move out of this simple schema and build more complex structures. Some of them, for example, something that happens in those computer vision problems is that sometimes they take the image and the colors goes in one direction, and they take some other image that is the gray scale of that, and they inject that with another set of networks. Yes, I cannot hear you because I don't have any speakers on this computer. This computer is from this desktop that I'm using here, and they don't have any speakers, or I don't know any way of activating something. So sorry about that. I will not able to hear you. So what else? What else I would like to show you? There are things that I will have to skip due to time constraints. Let me see here. Well, more of those ideas. Connecting here, one hidden layer. This one is receiving one input here from this one, and this other input here is just inserted with a concatenation from the output of the second hidden layer. Those are things in, that could connect in various more complex ways. And here I'm training, but that's not the purpose of training. And the third way of that of building those networks is by subclassing the master class, or a subclass of the model, and that will give you also more flexibility. So notice that at least those frameworks. So Keras, which is the official high-level framework for TensorFlow, start being very modern in the way they program those things. So they give you different ways of building those networks with increasing level of features or flexibility, but also keeping you an easy way of doing it if you want to go simple or you are just starting. So this one is the most complex way of doing this. Here, we saw this for those who attended the afternoon during the morning. For that example that I offer you for the quaternions, that we define classes and we define the constructor class. So we are defining a class here that is a subclass of this one. So it will be inherit all the properties methods from this class. So that way, this is for all purposes a model. Here you in the constructor, well, you put this. This is something that you always put on so construct the parent, and after adding the layers inside here in the constructor, and here the method. So here will be the different layers there, and here you override the call. Here is where you construct the connections of those. So again, this could go complex. Unfortunately, here I can see the train that, and at the end, well, we'll see the model there. Okay. Final thing here, I think for what I would like to present for this one will be the saving. So there are 2 points where we would like to save. I think here I'm just presenting, yeah, the clean saving. So the saving of the final model. Probably for another framework, I also will present another kind of saving, which is the checkpointing, where during the training you are saving the best model with the parameters that were the best. So the purpose here is simple. It's just saving all those, saving the models or saving the weights. So next time you can train them. So here, in this example, I am just creating a sequential quickly, and I am saving here the model. So the model is all that connectivity, all those, this layer is connected to this layer, is connected to this layer. So it's saving that in a format that I also mentioned in the Python in the afternoon. The one of those libraries, HDF5, which is a standard library for storing large amount of numerical data. So it's right there. And here we have the model. So we can do predictions because now when we load the model, we have the capability to just recreate all those weights. So with all those weights, this model is able to produce result. And this is actually what you store on the cell phone. The cell phone will not be used for training. We just use that for running the network and producing the results out of that. So a few megabytes of parameters is okay, and the operations are so simple that the cell phone today can do it. And here I'm just saving the weights. So you can just save the weights, you can keep the same model and change the weights and test with these weights, with this weight. And sometimes you solve this yesterday, that they're in those places where you see weights already pre-trained networks, they have different versions and they announce the accuracy with a different train set. So you can keep this one. I will be able to train that. I will not be able to teach you something that is more advanced, that you can take a network with the weights, remove some of the weights, and train what is left. Train those that so they start doing a little bit of magic with those things. So taking and fine-tuning a network that was used for something else. So here I'm just cleaning, just to delete. I would like that my notebooks at the end and put everything in output and remove that just to have something clean. I'm still not successful, and I still have to remove some. And here, yes, I have the callbacks here. I was thinking that I didn't have it. So here I am doing something more. So here I am adding this thing here. Notice is a checkpointing. So I am indicating that I would like to make checkpoints in this file. So those are just the weights. And saying, okay, say the best. Because sometimes, I told you, when the learning rate is too high, they will go up and down, up and down. It will just keep the best model up to that point. And you store that in the history, and you later on, after the feeding, I think, what I'm doing here is loading this and evaluating. So yeah, so I train, I store the best model at some point. And so that's what I do, for example, when you're running big, which is something that I will show you in a minute with CFAR with the MXNet. And you run, for example, for 1 week. 1 week is not enough, but you are using checkpointing. So the next time you just submit a new job, non-interactive jobs on the cluster. And here, what I'm doing here. Okay, I was retraining that. And here, I am building again. I am taking the values. Oh yeah, restoring it. Okay. So you see that it went up to a certain point, I stop, and I can continue if I need more epochs to get it right. So that is the evaluation. So after I got it, and here I just cleaning my space, cleaning all those models that were created. So that is with TensorFlow. Okay. So let me see what we can do. 3 minutes. In those 3 minutes, feel free to relax. What I will be doing is closing this and open a new notebook with PyTorch. So that's something that you can do. Otherwise, I will be I'll let you 3 minutes until I change my background here. So I will deleting this. I will killing this.
Here, there's someone who had a question.
Yes. So yeah, see, we are transferring to a different domain, which we're transferring to a different domain with each layer behind the concatenated document. Well, not something, as far as I know, not something. Well, there are some developments in the theory for people in computer science who work on this from the theoretical side, who try to what is called explainable artificial intelligence, because many of those models work, but nobody knows. Well, it's hard to know how they work or why they work the way they work. So there are some efforts on getting a way of explaining that at different levels. Some of them are variational methods, so where you are basically doing some tailored expansions with the networks and playing with that. That's one thing. But what I think the question is why you build a network one way and not in another. So most of that is intuition, educated guesses. So what you are trying to do, and at the end, after those educated guesses, trial and error. So it's a sophisticated, a more sophisticated trial. You don't just there is a compromise, you know, that you don't want to put too many parameters. First, because it will be expensive. Second, because it will give more chances to the network to start overfitting. For the convolutions, the reasons behind that is because we are in front of an image, and an image have translational invariance, and you want to preserve the translational invariance. So that's why you are using preserving the grid shape of an image and putting those wakes on top with the convolutions. We are able to capture that, and you are using the max pooling just to start changing the game from images or maps into putting more features for smaller maps that are capturing a bigger picture of the map and trying to fire back a bigger section from the input in deeper and deeper layers. So there are things like that. When we see this for the recurring networks, we will see, if I have time today, that if you try with a dense network for something that is time series or sound or words or things like that, dense layers will not work. Convolutional networks, which you could use, for example, a 1D convolution, will not work. It will actually be worse. So there is another solution, which are the recurrent networks, which are taking some memory from the past and injecting that memory into the network. So the next layer is kind of a dependency on the previous input. So that is like an internal loops there that fit very well the idea that you have with time series data. So different networks for different purposes. And by the way, don't think that just because deep learning is like a hot topic, this is just a hammer, this is just a tool. And you only have one tool, you start thinking that everything is one hammer, everything will look like a nail, and it's not like that. There are some other, right now in machine learning, what dominates for deep learning are those deep neural networks. For shallow machine learning, there is something that is like this, XGBoost, which are basically a more elaborated random forest for those very familiar with that. This is many problems are much better using XGBoost that they could be with deep learning. So deep learning is not the only solution that you have. So pay attention to this one. If you see in Kaggle here, this is a popular website for machine learning, where you can pick examples, you can pick data, and they offer, you can search for some data, so you can see your cancer, for example, and they have some training data, so prediction for breast cancer images, things like that. So you can pick ideas, notebooks, things like that. They also solve problems, and somebody made the statistics of that. Many of those are solved with XGBoost. Most of the convolutional time series are solved with deep learning networks. So keep in mind that this is not the only thing that exists. So yeah, those rules are educated guesses plus the spec. Okay, yes. So this time, the previous one was using TensorFlow. What I will be doing is changing this for PyTorch, because this is the next notebook that I will be showing to you. So Singularity, Python version, we will be using Singularity. For those who want to see the PyDocs, the structure of those networks with the links of that, use this one and re-execute the notebook that I executed before. So the C Python 3.10. But no, I will be using the Singularity community GPU Inter. So I will get some GPUs, 4 cores, and 4 hours here, 8 cores, 1 GPU, and here PyTorch on launch. And now we'll be running this one. Let me see here. So this one is for PyTorch, another very, very popular framework for deep learning. So what I'm doing here is loading PyTorch. PyTorch, they kind of subsections. So as I will be doing something with images, you also need, or you want to use Torch Vision. They have also something called Torch Audio for more like time series things. What I'm doing here, probably. Okay, forget about it. And I think, yeah, queue the device. Okay, I am just checking directly with a command line that I'm again on a Quadro P6000 and 48 gigabytes of RAM here, and no, nothing is been running there, so that's okay. And so those are the versions that I'm using. So here with PyTorch, we are really, really close to what the last way of building networks we use for TensorFlow. That's why I put it the second here. So you are actually overloading a network and an object, and in this case, a module. So here, the idea is the same. The constructor will have the layers. So here I'm having a convolution, a dense layer here. And here I am attaching those one to another to get it. So this is how this looks like. Let me see, probably will skip for at least part of that because I would like to jump into have time to show something better. Okay, one example with MNIST, how you build that. This is the convolutional MNIST. They have, in this case, the SGD is an object from the opt-in. So you notice that there are some things that are really, really similar between those frameworks. How I say, skipping these things that probably we saw here. Oh, here I'm training. So in the meantime, while I training, I talk about this. So here I am saving the state. So all in the weeks at the end. And here I am building a network, loading the state. so I can continue or do inference in this case. My experience is that PyTorch is, well, it's not just me. Many people say this. PyTorch is more Pythonic, so it's closer to what you expect working with NumPy, working with the different tools that are being created for Python. So they look that way. Compared with TensorFlow, which comes from an older history, so those things are not adapted as clean to the Python way of understanding things. That's one difference. Another difference is the PyTorch is usually slightly slower compared with TensorFlow, and probably MXNet is faster, but I need to double check if that have changed or not. For, let's say, some see on a website if someone did a benchmarking with CFAR 100 or something to see if one framework is better. So this one is good for learning. Is you get a good understanding of those networks, good flexibility on that. I don't think that is particularly fast, but that's okay. It's not something I will complain about. But that pretty much covers what I was doing before. So that you can here take an object with the class, change a few of the methods, pretty much in the same way of this as the subclass in TensorFlow, and you operate with that. I will not be making too much beyond this because I have another example more in depth with PyTorch for the in another node. So I would like to skip this and move into another one. And this one is one example that I would like to work in detail. This is for MXNet, so you don't see this so often. And I will show you, after we understand what the notebook is doing, how you create a submission script, a Python script that execute this, the code, how you submit this to the cluster. So this is for those who would like really to start training things. This notebook will help you. And it's right. What is this? The learning. Okay. No, notebooks. So it will be. Oh no, I have another book. By the time. I probably will go into this one directly. You probably will have some things that became confusing, but we'll see. We'll see. This one is something that it's just a new notebook that I introduced. And by the way, I didn't have time to work the notebook entirely. So what I did was to pick from the original documentation. So I had the reference. I cannot claim that everything. So I just took from the documentation. I am just introducing some changes to the notebook to make it clear in some point. So, so this one is running with MXNet. Let's see if I did it right. Okay, so here I will be using a different data set, which is highly used for computer scientists, for testing, for ideas. So it's slightly more complex. It's still 60,000 images. This time the images are 32 times 32. They have colors, so they have 3 channels per image, no longer grayscale. That's one thing. And those images belong to 10 classes. those like animals, different kinds of animals, cars, boats, airplanes, things like that. They are separated in 50,000 for training, 10,000 for testing. Those are the classes: airplane, automobile, bird, cat, dog, horse, those kind of things. So here I will be explaining to you a model that works for this particular case, more complex. It's a convolution with a few other things. I think it's a receiver. Yes, it's a ResNet. It's a ResNet 20, so it has 20 layers. There, the network, so they already have those models pre-made, and you can take them. So I am taking the model. I'm not taking the wicks. So I will be training the network actually. But all this structure that you see here, when we have convolutions here, convolutions and connected here. Well, if you count those, they have 20. Let's see the data for a minute. This is something that I introduced. So I will be taking the data that is already there. So also I took again, we don't have internet here on the compute node. So I took the data is called C410 binary, something like that. So it's right there. And I'm taking 120 images. So those images, again, they are 32, 32, 3. In MXNet and MXNet, I think it's MXNet and PyTorch. Their channels are the last index, the last axis in the tensor, while in TensorFlow is the first axis, or well, after the batch section. So that is one of the difference. Also, I put some functions here for making the plotting. So those are the first 120 images. So from the data, they look like this. They are really tiny, and even worse, what I did so this become visible is that here I am resizing those images. So they became 64 times 64. Otherwise, they are so tiny that I could not able to present those here. So they are really, really tiny images, but still, from far, you can, as a human, you can distinguish those. So the idea is that a computer can do the same. And I am doing something here to those images is include data augmentation. Data augmentation, I will not go into the details, I will just comment here. What it does is usually you are not so lucky to have 60,000 elements, things for testing and also for training, all of that. So what you can do is to reuse the images by applying functions to them. So you can take an image and do some rotations. So a cat that is rotated is still a cat. But for the network, it will start building some robustness on a way of identifying that. Another thing that you can do, for example, for a car, for those, let's say you have a car, you can just flip it. So you make a mirror, apply mirror symmetry to that. It's still the same car, so the network should be able to pick that, but it's a different network, it's a different image. So that with those things, with random rotations, flippings, sometimes some stretching, you get variations of the image that you can use to give more input to the data when you are short of that. So that is what I'm doing here. I'm cropping, I'm flipping, and also I am normalizing the data, normalizing those images. So here are the means and the values. Also because usually those images, I think it's also from vision, but I'm not expert in vision, in computer vision. So the different channels, they have different means and variances. So they are trying to normalize the different encoder channels. That's my understanding why those numbers are not the same. And that's what I'm doing here. And here I am creating batches. So what I'm doing here is that when you are training that, you are making batches. So a small collections of images, but you don't want to copy that data over and over for making that train. So what you do is to create an iterator in such a way that this object produces batches of images directly from the original tensor as needed and as many times as needed. So it's an iterator that will just throw new and new batches. So you see here with this data loader. The other frameworks offer similar capabilities, but in this case is Bloom, which is the neural network central object for the central module for MXNet. And so here you are saying, okay, take the image from this, apply the transformations that we saw up. So those that were defined here, and shuffle those. So then every single time you present a new batch, it could be with different order that will give the network the ability to change and train differently. And when a batch is used, those are discarded. So the next time that you pick a new set, it will not be from that, will be from the subtraction of that. And same thing for the validation data. So it's a machine that will produce sections of that. What I'm doing here is setting the learning rate. Actually here I am setting something a little bit more elaborated. It's something that is changing the learning rate over time or over epochs. So yeah, so gradually decreasing the learning rate. Okay, let me see if I execute it. Yes, so the softmax cross entropy loss for a classification, and I have this. I have my validation on that, and here I am actually doing the training. So it's going here, I think. So you see all the ideas that goes into executing this notebook, from taking the data, declaring the transformations, building a feeder of those data loaders. Of course, building the network was already created. It was a ResNet 20. And here I'm training. Yeah, I start training. So notice this goes slow. I'm still using a GPU, but this is not so fast. I was kind of going high. 20 will take a while. I will not wait. I will probably just let it move. And saying that the website from the documentation, when I took this, they recommend 240 for training. So I will not have time here to show you that. And if you do with 240 epochs, you will be getting this for the training and validation error, so 1 minus the accuracy, and something like that. So the error, probably it was, okay, I know this one, the difference here is with and without augmentation. So just the data, not doing the transformations. So without and with, you see that the network became better and recognizing the objects, because you are basically faking a larger variety of things. So here at the end, when they finish, you will take more minutes to do that, and I will jump and I will show you this from a different perspective. it will just store the values so I can take them back again for making more trainings or for just present that I got a solution that is doing what I want. So that will be part of my research. So part of my research is classification. Well, that is doing what it's supposed to be doing. So what I would like to do now is to go here inside Jupyter here in from here, if I can, and open a terminal. Let me see if I can go here. Hope this is big enough. And here on my Scratch, what I did, deep learning in the scripts, you will see a Python script. And see what it is this one. And the train C14. So I will try to show you. This is a rather complex. Eventually, if I have time, for some of you will be overwhelmed for what is here, but some of it will be happy because it will include a lot of things that will be useful. So this is a Python script that includes all the training. Not only that, is capable of receiving from the command line arguments that will affect the parameters of the training. So you don't need to enter in the script, changing the parameters by hand, because the kind of things that I want to change, they will be just arguments from the command line. So I will just inject in those directly. So for that, well, of course, I will be using some files. So I need OS, SHUtil, matplotlib. I will be running those non-interactively. So if I need to do plots, I will not be able to open Windows. So I will be using a different back end, and this back end help me to create PNGs, PDFs that eventually I can use for publication, but it will not try to open Windows during the execution of this script, but it's still able to create those plots. So NumPy, the standard, I will be using argparse. Argparse is the standard for getting data from the command line. I will use also logging for a couple of things. And everything else will be MXNet if you want, all that. So I am building a parser for the command line. That's the way you do. You can check, this is part of the standard library, so you can check in the documentation for the standard library how this works. So I'm changing the batch size. I'm putting a default of 32, but I also have the ability to change that from out of the script. How I also can decide how many GPUs I will be using. I'm being flexible with the number of GPUs. By default is not using the GPU, so we're running CPU only, which is the model, how many data workers that will be injecting the data, the number of epochs that I will be using, the learning rates, momentum, if I will be using momentum or not, a bunch of other things, and some things that I also introduced here, which will be the location where I will be saving the plots, which is the location where the data will be, the original CPAR data set, and which is the output folder where I will be putting at the end all those weights. So the data, the output, where I will be saving the plots, and some other parameters, if I will be adding more stuff. So this is the parser. So what the first thing that I will be doing is taking the parser and reading from the command line. We will see that when we execute this for real. Deciding here, okay, the batch size is the value of the batch size that you give me, the number of GPUs. So I will be collecting the parameters from outside, from the command line that I will be using for the network. And here, this is the input. This is the data, a tar with all the images here, binary. And what I'm doing here is copying that to the location where the data will be processed. And if the file is there, I'm just throwing, raising an error. And okay, here's the transformation. So all that was in the notebook, the transformation is there. And here for the test, for the training, how I select the data loaders, here and here. And what else here? And here is this section that was actually doing the training. So it's pretty much copy and paste from the notebook right here. The only thing that changed was the art parts and the extra arguments that I add. And here is just calling the main, it's the typical form from a Python script to call the main function, which is what is right on top. This is the part. This. So it will call, it will execute. So if I could, if I want to do this from the command line, still running something like this, not using the Jupyter Notebook, I can request an interactive job. I will show you that this and this, an interactive job with this command, qsub-I. I will be using the community GPU community GPU inter, that's the queue, and I will be requesting nodes equal to 1, ppn equal to, let's say, 8, GPUs equal to 1, and what else I need? And it will give me 1 week. It will take me a while to get this. If I do it this way, it will probably sit there for a long time. I don't. Oh no, I got it. I got it. Okay, I was like. So with that, you can go here, doing everything by hand. Module, load, singularity. So now I have there, I go into the Scratch, and what else I will be doing? Deep learning, and let's see, deep learning test scripts. So with this, now I can execute. I could do it entirely manual, so I will be using Singularity shell. Share containers, ngc, mxnet 0753zip. So I will be getting a shell inside the container. So you see there that this will interfere, but this is the terminal. This virtual terminal doesn't work nicely with that. And at this point, I will be able to execute Python 3. Let me see if I. Python 3 is because if you are doing this, you are not doing this from the virtual terminal like this. What is the name? Train, CFAR, and all the parameters. So if I want to remember all those parameters, I can use -h and fill in the different parameters for this. Let me see if all those. So you get like a documentation. When you build this with art parts, you get a documentation of all the parameters all used on this script. So this is a more professional way of doing a Python script. But I will not be using this, so I keep it at this. You can use it by hand this way and run, and you will be able to run for as long the wall time allow you. But I will be doing something else. I will be submitting this training with a job. And so here I prepare for you, for this case, for example, this one, which is the way you submit a job that will execute in the cluster, completely non-interactive. So that means that when you submit the job will not start running immediately. It will be in a pile of execution, and when resources became available, it will pick this job, it will send you to the right machine, and will start execution there. And when it finished, usually it sends you an email saying, I finished with the job. So here I am introducing some of those parameters that we use when we are building and writing a submission script. Those here, so the first one is the name of the job. This is a completely arbitrary name. And this one is because I would like to collect the output and the error, the standard error, the standard output in the same file. Here is basically the same line that I requested before. So I will be using 8 cores, 1 node, 3 GPUs. And I was testing this yesterday to be sure that this is working as I want. So I was using a queue where I have access to. So here I am putting some variables that I will be using down below. So the names, which is the image, so the location of the image that I will be using, the location of the Python script that I just showed you a few minutes ago, and where will be the location for the outputs. So I always think, this is just best practices. Think about keeping the input in one place, so the data, the input in one place, the output in another place. Hopefully with some metadata, so you remember what you are doing, what you did with that to create that output. And sometimes you can separate another folder for logs or things like that. So that's what I'm doing. I will be actually separating the log file. And the location of the data. So that's my input. So I have my input in one place, my script in another place, my output in a different place. So I'm executing NVIDIA SMI just for me later on to check which was the machine that actually executed my job, or which was the card, the GPU card that I used at that moment. And I am loading Singularity here. I am using Singularity exec. So I will be executing a Python script. This is important for Singularity to be able to see the NVIDIA card. So you need to put --NV. I know that this is fast too much. This is kind of advanced topic. But for some of you who would like to see this in this workshop, I am just taking some minutes to present this. This is the image. So this is the NGC MXNet that I will be using. I will be executing Python 3. This is the location of the Python script. This is variable is this. So I will simplify. So to make this shorter, I replacing that here. And those are the parameters that I use for, or maybe I need to do it smaller. But it will break me the whole thing. Great. Yeah, there is no way looking. So here, so the epochs I will be able to now request the 240 or more for 1 week. 3 GPUs. So 3 GPUs will be working on this problem. They will receive different batches of data, and they will synchronize the wakes at the end. The batch size, so it will be, the definition of this is 96. So that's the batch size per GPU. The learning rates and how the learning rates decay, so how the learning rate becomes smaller and smaller with some at some specific epochs. So the idea is to request here 240. So when you reach 80, it will lower the learning rate. When it reaches 160, it will lower it again the learning rate. So you are making a smaller and smaller jumps because you are now landing in a very shallow surface. So you want to keep the details at the very end. So that is something that also helps performance. Where are you storing the data? Where are you storing the output? Is this place? They say I am using the same output just for the same place for storing the output, for storing also the plots. The plots will contain the accuracy, all that. And also this trick here at the very end. So this is a long line in shell, in bash, in shell. You can put those, so you make multiple lines, but this is just one long command line. It's a long command line. At the end, I am redirecting both the standard output and the standard error into a file like this. They have the same name, .log. So I will be able to see when this starts running, I will be able to go there, open the file, and see the epochs and see everything is going well or not. And if I am not satisfied with the behavior, I can go connect to the cluster terminal and kill the job and do the adjustments that I see fit. So that is how you build a submission script. So the final thing here is submitting the job. So queues up. So I can do it here. I think it's okay to do it here. I was doing it here, so my files will be in a different place. So you put queues up. But you don't do it this from the compute nodes. At this point, you should be on the head node. So now I will be submitting the job. Queues up, share, is actually Scratch, Franco, deep learning, scripts, and run job, 3 GPUs, PBS. So I am taking the submission script, offering that to QSUB, and when I submit that, I receive a number. That number is a unique identifier for my job, and I will be able to check with qstat. This is the complete command. Which are my jobs in the system? You will see this one. This was my job. And I submitted in a queue where I have quick access. So this job here is right now running, has been running for 15 seconds at this point. This is the name that I put to this job. I request one node, 8 cores, and this could potentially be running for 336 hours, so 2 weeks. Again, you will see this. I programmed this with just 20 epochs. I think it takes like 5 minutes to complete. So probably last. It was 5. I think it was 5 minutes when I was using the 3 GPUs. I don't remember what. Now, but that's the idea. That's what I would like to offer to you. I know this is kind of more advanced, how you take all those notebooks, convert those into a Python script, how you write a submission script that allow you to put those non-interactively, and you can submit many jobs. No problem with that. You can submit 100 jobs. So maybe you are exploring this and you have an idea that, well, I will be exploring this with this number of convolutions. Maybe I will be trying a slightly different architecture. You can try many jobs, and they will be entered in execution when resources become available. On this cluster, we have like 20 or 20 something GPUs available. In the new cluster, we will have a ton of GPUs, so we will be able to run this massively. What else? So I think we can skip here. I think, but by that time, this have complete. You will see from the Jupyter notebook that I execute 20 epochs, and you just see the tail here of the training and validation errors, and you see how this is going down, and so everything looks fine. But what they say is, okay, if you want to do it right, you should be using 240, and you will see very clearly here this feature. Why we see this going down? Because exactly at this point and exactly around this point is where we are decreasing the learning rate. Those are the points, and it's going one order of magnitude smaller. And let me see if I can pick you exactly where they were, those parameters. Yes, here. So up to 80, it will go with this learning rate, because at the beginning, those wakes are crude. So I am happy jumping that, it will be jumping like a drunk. And after, it will go slower, so it will be going refining this. So at level 80, it will go into 0.01, and it will go into 0.01 up to infinity. So up to the maximal number of epochs that I request. So this is a nice example of something, let's say, kind of more advanced, and the way you submit those here. I will still activate this so this don't die. No, it's complete. So now it's complete. I know that it's complete because I see this C here. This C here for this job. So all this line here is the line for the job. I will see here that is complete. I also can inspect this. So if I execute check job B610578. Yes, yes. So you will see some information about this job. So you see here, for example, okay, the job, this is complete, my account, my wall time, it took 3 minutes, 49 seconds. Out of those 14 days that I was allowed to run this, the amount of memory, this is CPU memory, so it's not taking account the GPU as far as I know. And the number of CPUs that were used, not much, because for this, all the processing was happening inside the GPUs. So the 2 GPUs, just 2 CPUs were actually doing something. That's typical from this kind of jobs. And that pretty much, that's it. 3 GPUs here, 3 GPUs, 8 cores, all that. So that is one way, and this was the machine that did this job, which actually very good, because probably that's why it took so little. So this one is the file that will contain the way that it created both the standard error, the standard output collected in a single file. That give me not much, because everything will be in a different file, but the execution of NVIDIA SMI. So I will see that here on this machine, I got 3 GPUs for me for this training. So I will be using the 3. Everything else, I put it here on my Scratch deep learning output. So I put it here, and where it is, I think it's this one. Let me check the dates. Oh yes, is this one here, the log. Let's see. Oh yes. So those are the logs. This is the output of this training. Well, the same which were first, or this is just log from the parser saying, okay, the parameters that were used, which is a good thing. You should always do something like this. Keep all those parameters. So this metadata is important, because eventually you want to recreate this and have a baseline for this. So those are all the parameters that the parser receive are there. So for your recording, those are messages from using the libraries behind this for CUDA, and this is the actual train. So the actual information is right here. All those training, validation, losses, all that is right there. And when I execute this for 240 epochs, of course, it will take a long time. So I will be able to log into the machine, go into this file, and see the progress of my execution. And I can return in the afternoon and see if it's going better, if I should leave it as it is, let it continue, or I should just kill the job and do some changes because I'm not happy with that. That is it. So that will give me excellent time. So that's one of the things that I would like to show you. Let me see if with the time that I have left, I will probably go into, let me see if I use this one. If I fill gaps here with this one or not. Probably will skip this notebook. There are better things to say. No, I will skip this notebook. I will skip this one. I have far more material that I was able to present. And now we'll skip entirely this for sure. Those are advanced topics. You can go check on them. Things like inspecting, if you want, inspecting the weights, inspecting what, so to answer the question, what, how the network, the kernel looks like, what is the mappings, the internal mappings of the networks when they move inside. So start doing some surgical inspections. Deep inspections could guide you into what the networks do. So those are advanced topics, and those are for TensorFlow. So I will skip in that. I will be reiterating back again here with the convolutional neural networks again, and I will be executing this couple of notebooks here. So this one is probably just fine. That runs still on the MXNet. What I can do is, let's see, let's pause for 5 minutes so you relax. You can go to the bathroom, restrooms. Sorry. And I relax my thumb. So, and we continue with this one. We'll see how far we can go with the neural networks. For the afternoon, we will be running some other notebooks with convolutionals. And I hope I can at least do the first part of the recurrent neural networks, which is something that has potential scientific applications. So that's something that I don't want to see. Questions, if you want, I can entertain questions from you online. So we have 30 people online. I am very happy that 30 people plus 6, 8, 9. So we have around 40 people out of the almost 120. So that's 1/3. That's excellent. So 1/3 of the people survived to this point. I'm very happy with that. We will see. Don't forget about filling. I think Kyle have sent you the form, so I could learn what I did right, what I did wrong, what I could do better. For the next time. Again, this is the first time that I'm doing this. Você é brasileiro?
Sorry?
Você é brasileiro?
So,
Não estou brasileiro por aqui. Eu escutei você falar. Então, esse é
você é colombiano.
eu colombiano. Mas minha esposa é brasileira, então.
Ah, verdade.
Então, você é de que faculdade? Você está fazendo doutorado aqui?
Eu faço doutorado aqui.
Em que? Que
Engenharia aeroespacial.
Aeroespacial.
Mas é robótica. Lá na minha universidade no Brasil,
Qual universidade?
na USP,
USP?
tinha bastante bom. Quando a gente veio aqui o primeiro dia, eu falei assim, uai, ele tem nome latino, mas ele tem sotaque de brasileiro.
É brasileiro? Mas fala português.
Não, é culpa do meu filho e minha esposa, né? É que ele fala o tempo todo, ele fala em português, ele passou um ano em Portugal, um ano crítico da vida dele, quando estava em segundo ano, ele passou no Brasil, então ele pegou o idioma e ele não voltou atrás. Ele em casa ele fala português para mim, eu falo espanhol para ele, ele fala português para mim, com um monte de inglês metido no meio, mas ele fala, e por minha culpa, ele introduz palavras dentro do espanhol que a mãe dele corrige. Eu disse, não, isso não é assim. Não. Meu filho fala uma mistura de portunhol-inglês.
Interessante, fala 3 línguas então também.
3 letras, fala 3 línguas.
Em casa, o meu pai é espanhol. Então,
ele é hispano? Ele é latino?
Não, ele é espanhol.
Espanhol.
E tinha uma situação relativamente similar.
Então, vocês dois são da USP?
Não, eu sou do Rio Grande do Sul.
Vocês são. De onde?
Santa Maria.
Santa Maria? Onde que está?
Rio Grande do Sul.
Rio Grande do Sul.
E sua esposa de onde? Qual estado?
No Nordeste, Natal. Mas eu estive 2 anos no Rio, fazendo mestrado no CBPF, sobre física, Instituto de Física Teórica, fica na Urca. Estive 2 anos lá. Eu tive colegas do Sul, do Sudeste, obviamente, e alguns do Nordeste. Então, sim, tenho alguns amigos, boas lembranças daquela época. Eu estive lá em 2006, 2007, metade de 2006, 2007, eu saí de lá para a Bélgica, eu fiz meu doutorado na Bélgica. Eu falo francês também. 2008. São 2 anos que eu estive lá no Brasil.
Casou?
Eu casei. Tenho meu filho. Meu filho nasceu na Bélgica. E bom.
Assim, tinha bastante gente no meu departamento que é colombiana.
Sim.
Depois de brasileiro, era a segunda nacionalidade mais comum lá.
Sim. Era uma boa época que ela criou, que eu estive, porque era na época da Dilma, e ela tinha muita grana em termos de bolsas, tanto para os brasileiros sair fora, naquela época, como para estrangeiros latino-americanos ir lá, e você recebia na bolsa que dava para levar, né, para sustentar. Era uma boa época, né? Foi bom. E aí já... Não,
aqui você é professor?
Aqui não, eu cheguei aqui como um postdoc no departamento de física. E depois peguei já uma posição técnica, por dizer, como software developer, research computer software developer, o que significa que eu ajudo as pessoas que têm problemas.
Você está responsável
por ser uma conexão entre o cluster e
Como funciona para criar uma conta no cluster para poder usar mesmo a gente tem direito, então, a usar essa community views, a gente tem direito de usar, então, de graça.
Sim, de graça. Sim, sim.
Eu entrei ali no formulário, tem que preencher como que é PI ou não PI.
Okay, yeah, I can switch to back to English if someone is listening to that. So yes, you can request an account with us for our clusters. We have 2 clusters right now. We will have a 3rd cluster by the end of the year, maybe beginning of the next year. So you go to helpdesk.hpc.wvu.edu. So you go here. So if you want to see it, I can show you the helpdesk.hpc.wvu.edu. So it will say, okay, public research for WVUs, your students. So you go here, and what is the option you want an account? So there is request. Let's see,
User account.
new user account. Yeah, new user account. So new user account. You put your email. You put a summary. You say request an account on Thornflat, which is the newer cluster. Forget about, but on the Spruce we have a few GPUs, but those are old. This is an older cluster, so they have, those are, if you are familiar with Intel architecture, those are Sandy Bridge, Aswell, Dotwell, so like 6-7 years old, probably more. So it's an old cluster, and the kind of GPUs that we have there are K20s, K40s, so they are like 5-6 years old, probably far more than that. And so you are a student, so you are not a PI. So you need someone who will sponsor your account. So basically give you the approval that you will be using the cluster for legitimate purposes, who will be responsible for you and tell you when we need to delete your account because you finish your PhD studies and things like that. So you put the name of the PI, you put the email of your PI, you put the kind of project, the purpose of the usage of the cluster. So I will be working on this modeling this. So this is for us. So the bureaucracy behind that is for us to take those your information about the purpose of the cluster, so we can offer that to the funding agency, which is NSF, which give us like $1 million for this cluster. So we are using the money on this and this and this, and those are the papers that have been published as a result of the research. So that is why we need a title, we need a department, we need an abstract. There will be like copy and paste of the paper that you were working on for that. So the description looks like an abstract of a paper. So you go here, you comply that. So in your case, it's probably not a big issue, except something that for NASA that are secret. But in many cases, with the kind of things that you do, they don't have any, they don't require any clearance or secrecy or all that. For people in health science, it's slightly different. So they have more chances of data that is HIPAA protected. So health data that needs to be identified. So we cannot store that kind of data in our cluster. So we need to be sure that you know that we are not capable of offering the compliance for that security on our cluster. They have another cluster for that, for health science. And you acknowledge that you will be using for legitimate purposes. You will not be mining Bitcoins or things like that. So doing illegal stuff, those things are monitored. So in case you can get in trouble if you use it for non-legal purpose, and you send that. So the first step is your PI will receive an email. He needs to agree that he will sponsor the account to you. There are not costs involved in this process, and you get your account. After you get your account, you will have 10 gigabytes of space on your home folder, and you will have a quota of around 20-30 terabytes on a Scratch folder that you can use for your data. And you will be able to use the community nodes, the queues, so there are community queues for your jobs.
And then like the longer one is 1 week, right?
And the longest queue on the system is the week. So if you go here, this is okay. This was terminated, so I need to reopen a new one. I will be. Let me a moment. Let me leave all that. Clean this one and open this one. So I will show you quickly the kind of queues that we have. Queue stat. If you execute this command, use that. Oh, no, not this. Uppercase. Sorry, uppercase. So those are the queues on the system. So pay attention to those like standby, all that start with com. Those are community queues. So those are available for everybody, PhD students, faculty, staff. So they are widely available. Again, small memory is 90 gigabytes, extra large is 760. Week is the longest wall time that we allowed on for those community queues. We have also 1 day, which moves faster. And week, and there is one here for GPUs. So a queue for community using GPUs, which has a limit of is 1 week, if I'm not wrong. Those are the community, and this one, or a couple here with medium-sized memory.
Did the bug as well or not?
The debug is
Just
basically
like
for me.
this
This is a tiny. It's for me when I need to forget about that. It's too small. They don't serve any real purpose. A standby should be your queue to use for interactive purposes, for submitting the small jobs that you expect to finish in 4 hours, or you are happy doing checkpointing and running for 4 hours and restarting if you need running that.
Like, can we apply for an account even if we just like want maybe like to learn how to use and maybe test, like even if in the end we don't use in our projects, but I mean I'm gonna add like
Yes, you can do that.
but
Yeah.
It seems
It's an
really-
exploration for you. It's an
Yeah.
exploration.
It's very interesting, like how to
that you could serve-
like learn how to do that.
How to do that? You have a good machine. Those GPUs are expensive, so it's not something that you can buy in the corner. So you can explore those. And this is just, I mentioned that this is just one of the ways of doing, a popular way of doing machine learning, the deep learning. It's just one section of machine learning.
Yeah.
This is another thing that is very popular that comes from random forests. So this is what they call a shallow machine learning versus a deep learning. And there are many cases where this is the solution that you want to use. It's basically taking a decision, okay, do this with this probability, do this with this probability, do this. So those are opening, branching. You need to read more in depth at that. So again, all those things are there. For those who are into big data, we have also Spark. Spark is like machine learning, like scikit-learn, but you can use many cores for big amounts of data doing analysis, or eventually more nodes. So that is some more things that you can.
And what's the difference between the COM GPU week and the COM GPU inter?
Okay, this is for interactive jobs.
Oh,
so
okay,
this is for submitting jobs that run with Jupyter notebooks, or this other way where I queues up dash underscore I, uppercase I, so that jumps into for interactive execution. Okay. Those you pick, what is this? They call GPU week. So this one is for non-interactive jobs.
Yeah,
so
that's where you send
I didn't send that because I could use a different one just to get it quickly. I was using a different queue that I could use, but in general, I put that in the comments.
What about the sharing of the data? Like you said, like flows or something. I forgot the name of the program. Like it's like you said, like you use this rsync function, like how you share data with like a local computer, for example, like that. Like that function that you use at the beginning whenever like we use to copy everything.
You mean copy the data from your
Yeah.
computer?
Yeah.
Yes, you use Globus. You use Globus.
It's the I can show you. I learned how to do that.
Like it's just a
Globus.
wrap or
Is this so the idea is that you install a tiny program on a Mac or PC, Windows, Linux. This thing program will put one icon in one corner. When you click there, there is an option for opening a browser, and that we have one left side, right side. You go here, select your computer right here, select the cluster, and you move files from there. The transfer is parallel. They check at the end, and if you want, you can select that it's doing a synchronization. Also, you can do recurrent transfers. So they have all things there for long jumps, transfers. Yes. So let's continue. Let's go here and let me see if I can clear this. Okay. So I will be deleting this. And go into another Jupyter notebook. And I think I will be happy with this one. I don't think I needed anything special. Let's keep it like this. So I will be rounding ideas about convolutional neural networks. It will be the final theoretical side of that. So that will be my entrance point for two notebooks that will present more in detail the convolutional neural networks, probably for the afternoon. And I hope at the end I will have at least 30 minutes. That's my hope, at least 30 minutes for showing you the recurrent neural networks. I don't want to leave without at least showing you the long another NNN. Let's see, scratch. By the way, with this you can also copy files. This is another way. If what you want is to copy one file or to transfer one file, you can upload files from here, or you can download files from here. So let's say that I got in the output some figure, let's say this one, I can visualize it directly, or I can take it and download it. So it's okay for one file, for a couple of things, for big transfers, like transferring all those notebooks, and the data is 5 gigabytes, I think. It's better to use Globus. The transfer will be parallel. You will be sure that the transfer was okay. That's the solution.
Will it be downloaded into the local machine?
You can download it. You can transfer all the notebooks to your own computer if you want. With the data, all that, the training data, all that is there, and you can execute it. Just need to have the computer, MXNet, install TensorFlow, and the extra packages there. But that is okay. So what we'll be doing is opening the notebook, going into this rounding around convolutional networks. I think this is brief. This is not attached to any particular. Just rounding the concepts here. So for convolutional networks, what I would like to show you is, well, in mathematics, what a convolution is actually this function here. What we are doing is some relaxation of the definition. That is something that happens a lot on deep learning. We use a lot of terminology that is not mathematically precise. The idea of tensors, the idea of convolutions. So with some nuances, they capture the spirit, let's say. So in a convolution, particularly for when you are talking about a continuous function with domain in the reals, this is what you are actually doing. So you are taking the integral of one function with another function with the time shifting and the lag and running on the entire domain of the function. So what I'm doing here is the typical way you present those for those who are not. You see, no, I forgot to run this from the very beginning. So I will give you a little bit more of the ideas that are lying behind convolutions. So you see, so I am, just to give you an idea, I have two functions here. So this jump, for those who see or took any class on electronics at some point, you will see this is a very classical thing that you saw in those courses, and this triangle function. So I will be computing the convolution of that in the mathematical sense, and it looks like this. So basically, it's like taking this triangle and start moving from far away and start shifting that triangle inside and taking the account, the product of what is inside here. So at some point, it will start jumping. It will, the triangle will start entering. The value of the area behind that product will go up. At some point, it will become maximum. When you go here, so when you reach this point, the area is maximum. And after that, it will start going down. Will start going down, and that's a typical curve that you see in a convolution. Why we use convolutions? And so that, by the way, this is, so this will be from the mathematical side, from the equations, what we'll be doing with the images, with the pixels as a sum. So it's a sum with all those projections or sums. And the idea is that there are some symmetries, if you want to see that. And the fact that this is also similar to a related function, which is called the cross correlation. But in the case of deep learning, what we are doing is this. I probably already explained this. We have here the image, we have here the kernel. What we are doing is taking that kernel and overimposing that on top of the image, getting the sum. So in the thing that you should keep if you want to translate that into a dense layer is like having a dense layer where some of the weights are shared, are fixed. So some of the different weights in a dense layer, they are constrained in some way. So that is one way of thinking about that. Another way is, well, we have some ways here, no biases. When we are doing convolutions, we don't have any bias. And we are overimposing that kernel on top of the figure. We are computing this equation here, whatever is the result of that, we put it here. And for the last element, so we shift there to the final element, and we got those products here, and this is the final convolution. And by the way, you can decide how you move to the next image. So you can just go, and typically that's what you do for this, is you just move 1 pixel to the left. So the next time it will be this B, C, F, and G. And if you do that, at the end, you get an image that is, for this case, 2 times 2, you get an image that is, you are losing 1 pixel on one side, 1 pixel below. So you are loosen a little bit if you are not extending extending the image, so you can overimpose that in a different way. We will see that in a minute when we are doing that. So that is the idea, one. And the final idea that probably is better with the actual notebook is that this is really closely attached to the max poolings. And the idea of the max poolings, let me see if you can see this, is that make the figure with deeper and deeper. So one convolution is just trying to cover features that appear in here. The next convolutions will try to cover a bigger area, because we are doing is taking this, and the next image after the max pooling, it will be an image that is half of the size of that. So all those section here corresponds to a bigger section here. So you are taking a bigger and bigger picture of that. That is what you would typically do. Another thing that you see are things like this: convolutions of just one element. Convolution of just one element is basically the identity. So you have one number here, and you are doing the convolution with that, and the number is 1. Well, it's just the identity. That is something that is used for residual networks, where they connect the input and touch and go and inject it into down below into the network. But we use it without knowing in one of those pre-trained networks. But that's kind of more advanced. So I will be showing you the convolutionals with TensorFlow. So I will be launching this one here and going into Python via Singularity. Everything the same, except that I will be using TensorFlow. And I probably will kill this, delete this, and free some space here. So yes, Scratch, deep learning notebooks, and this one. So how we work with that in practice with TensorFlow. I probably will not have time in the 30 minutes that I have. So I will go up to some point, and I will continue in the afternoon with this notebook. So this notebook is big. So I will be cleaning this. And start executing this. So we will be using TensorFlow, and I will be using this library here for manipulating images, for basically present those images. So, okay, how we work with TensorFlow for this. So the basic thing is convolutions. In the case of images, convolutions to D plus max poolings. Those two are very closely used as a block. So in this way, so what we are doing is using the functional API, or again, in Keras. So we are declaring the inputs. Here we have a convolution here that receives the inputs. We have a max pool that receives this X. So we are reusing the X here because we don't need to keep the, at least not for this. So we will be injecting that one convolution plus max pooling. So, and the max pooling is size 2. So it's just reducing the image to a half, or half on each direction. So you will have a quarter of the number of pixels as an image. We are doing this here. So now this time we are duplicating the number of features. So duplicating the stack, the pile of kernels, so the pile of maps that we will be producing, but this time we will be working with an image that is smaller. So the kernel size is 3, will be 3 times 3. With Relus, this is typical when you are doing image recognition problems using Relus. And so here we have one convolution, let's max pooling, another convolution, another max pooling, another convolution. And the final one is just flattening the final array, the final pile of maps, and entering a dense layer with them, and execute. So this is how this looks like. So I will be shortly reusing this for a quick example, again with the MNIST case. So we remember what we are doing as training. I think this training is fast. Should be fine. So what we are doing, I think I present this in another notebook. This, imagine that the filter at some point during the training end up being like this with those numbers. So we take the pictures, we overimpose, we compute all these operations with all this corner of the points, and we will store in a number here too. Now we are taking here, for example, when we do the max poll, we have two, in one corner, we have 2, 3, 2, 3. So the maximum number will be 3, and that is what we are actually storing. This is the convolution, and that is the role of the max pooling. So it's basically saying the feature was around there, pixel, 1 pixel to the left, 1 pixel to the right, but it was there. That is the idea of the max pool. They have many arguments that you can elaborate for that. The strides, typically those are ones, at least for this kind of problems. But remember that you can do, you can move to the right or to the left or down with bigger jumps if for some reason you need it. You select the activation, usually Relus, and there are some other things that you can add to that. So this is the architecture that we have, nothing that we would like to minimize the final dense. That's what we are doing. Those max pooling too. That's another reason for doing the max pools, is that we are reducing those. So we end up with something that is manageable, at least for the MNIST is a reasonable number of elements. So the max pooling here, yes, so it's just returning the maximum. And this one is showing, this was, I did it before. What happens if we are not doing the max pools? So in this time, we are not using the max pool. So you have the convolution and the convolution to the next one. So we have several problems with when we are doing that. One, you will see an explosion of elements in the final dense layer. When you convert that into a dense layer, it will explode. And second one is this fact that this convolution, it will be just taking a narrow section of the image because they don't have time to propagate further and further away. So you are losing the big picture when you are doing that. Okay, yeah, thank you, Kyle. Okay, so download the data. the correct number of parameters, I don't know. That case, I need to see you what you did or the network. I try to make sense by hand of the number of parameters that you should have. So here I have 28 times 28, so that is my input. So 768. So here I have in this convolution we have, those are 3 times 3. So we have 32 matrices, 3 times 3, to check if that give you this number. When you will have 64 of those, but this time for the image they will be smaller, so they will give you this number. And when we flatten that and we connect this, we should get this number. So we'll try to do it in math. Try to make sense of that math, but it will take me a while to do it. So what I would like to reach for this notebook is to show you how you solve a problem. By the way, this notebook is based, I think, in the Keras book, one of the books in the that they mention this problem, so they give you the link to what is the data set. This is not a data set, that is internal. So the problem that I will be dealing with is a problem with we don't have enough images to work with. So at that moment, we have several alternatives to work with. One is doing data augmentation. We mentioned that a little bit with the CFAR10 case, where we were doing rotations, flippings, that sort of operations. That's one way you can train the networks, even if you don't have enough data. That could be the case, for example, for medical data. We don't have enough patients. We're working with that, so we need to try to extract the juice from the little amount of data we have. Another solution is to extract portions of a pre-trained model and use them, or take a pre-trained model and just, for example, tune the last layer, for example, and everything, all those first convolutions are considered fixed, and the final are what you want to train. So because all those things that trying to capture features are pretty much a standard when you train those networks, trying to capture edges, curves, things like that. So this is a file, it's a zip file that contains a bunch of photos of dogs and cats. I prefer not to uncompress the image, so I'm doing all the processing with the files, uncompress those internally from Python. So I'm showing you just one of those images from the dog, from the cat section, from the cat folder, and I am getting the one, for example, from the dog section. The images doesn't need to be of the same size, so this is just a collection. I don't know exactly how many they are. This was for a competition in 2013, so almost 10 years ago. And let me see how many we have. So the data is not so big. I think I think it's 2,500. Yeah, no more than that. It's relatively small. So not 60,000. We don't have the 60,000 digits. So this is a small set. So again, I will be using the functional API to build this stack of convolutions, max pooling, convolution, max pooling, for how many? 1, 2, 3, 4. 4 blocks of convolution max pooling, final convolution, flattening, and moving out. So that is what we have. This is the number of parameters that we have. Notice that on max poolings, no parameters, it's just taking the maximum. You can think, why the maximum? Why not the average? The average will not give you what you want. It's like you see the feature is here, but the feature is not when you move 1 pixel to the left, and not when you move 1 pixel to down to the right. So you will get something like the feature is more or less there. So you are not getting the idea of that the feature of an edge was captured on that corner of the picture or that particular location of the picture. So the max pooling, that's the reason behind the max pooling, is saying the feature that I would like to capture with my kernel was there. Pixel plus, pixel minus is there. So a total of almost 1 million parameters, which is big. So I expect we will eventually will have a lot of overfitting. When you see this amount of parameters, that's typically what happens. We will be using a slightly different optimizer, cross entropy, and the accuracy. So what we'll be doing, again, this is something similar to what we did in the case of MXNet, but this is how you do it with Keras in TensorFlow, is that you want something that draw for you batches at will, without having to build those and allocate memory for those and waste time of that. We just built a machine, like a tiny machine that just throw batches of images when we request the next one. Give me the next batch, and the system will pick those and give you the locations in memory where you can take the portions of that. So that is what you are doing here. In this case, those portions are from all those images, which are actually files. So it's building a machine that throw you batches after having read all the images back to your to memory. So we have here the files, the classes, and so you see here one of those. Oh. Okay. So when I pick one of those batches, it looks like this. So it will be 32. This is the batch size. So this is the number of images that I will be using. Those are a 180, 180, and 3 channels for the colors. So that is the way in TensorFlow we put the channels at the end. And the labels. So if it's a cat or it's a dog, it will be a list of 32 names or 32 numbers to identify 10 cat dog. So that is what we are doing there. We will be using a callback for storing the partial results during the training, just saving the best. So you see here, still where I'm using the GPU, so those go relatively well, fast. Remember, we are training what, like 1 million parameters there. And it will take a while, but in the meantime, I will try to continue the discussion here. It will not be plotting this, but at the end, it will plot the accuracies, the losses, and we can evaluate this model. So this will be my baseline. So what happens if I am just offering the data that I have, the original data? Now, I think it will finish. 2 seconds. Yes. So the history there. So you see here the accuracy that we are getting with the training data, really high. We see a saturation point here. Validation accuracy after epoch 7, 8, maybe. This is no longer improving for the validation data. Losses is telling us from a different equation, pretty much the same story. That at some point we are actually getting worse on that. And this is the accuracy that I'm getting on the test data. So it will be 68%. 68%. So of identification will be right. Okay. So now I will be introducing some augmentation. So some of those things that I would like to do to the image. So one of those is rotations of flippings. So they will flip, and they could also rotate at random angle, and also they can zoom in or so they can make the image bigger, farther. That is the kind of things that I would be that. So the same machine will here start producing batches where the images will be transformed all the time with that extra with this function. So you will see something like this. So the same cat, so the same image, after you crop it, you center, you crop it. One of those could be, for example, flippings. So you are flipping this photo into this one. You are notice that here we are probably applying a rotation here to this cat. This one was not flipped, but probably the forward here, the second row here, the image was zoomed out. So we have all those kind of possibilities that could happen. It will take one image for every image that it takes when it's building the batch, is doing those transformations, and that is what is injected into the network. So what we hope is what the features that a cat has, like the pointy ears, the eyes, the whiskers, or all those things, our network is capable of identifying those, no matter if the cat is from one side or another side, if it's slightly rotated, all that, the features will be present. So keep in mind this figure, we will go back to this one. So we noticed that here we got validation, we were around 70%. And so here around 70%. So let's keep that figure in mind. So I am here doing some adding that, and I also adding dropouts, a dropout of 50. So that is the same network, but this time I am having some dropouts. And it will be right here, and I will be saving that with a different name on the output. So the best model, just in case I would like to regain the weights for rebuild this later on, is there. And I would like to check if I can get those. It will take me a while. So what I will be doing is start discussing the next one, because this one will run for a long time, and going into this one. At least not executing, but this. I can take another network that was retained, and this is a network BGG. What is the name of? I don't remember exactly what BGG means. And it will take me a while until I get those. The idea is that I will be taking a network that's been pre-trained. I will be taking the values here. Where did they have this? where I capture those. Okay, yes. Here are, I got it, then I already have here the wakes in HDFI from the network. I am using those in the network, and I am using here, when I run this one, you will see it will be much better. It will take me a while. Let me see. We probably will not have time to reach to this one because this one is taking. So what we can do is say, okay, so to this point, let's summarize to this point, and later we will, this afternoon we will start with this one. So the first one was the original network. This one here, this one here. So a collection of max pooling, convolution, max pooling, max convolution, nothing else. What we did after that was introducing, and we got these results, was introducing this augmentation. We put this as inputs for this new network here, which also add a dropout. And it will run for, I will have to let it run for a few minutes. And the message at the end is this network is significantly better in the accuracy just by playing with that augmentation data. So that's the first trick. The other two tricks are the pre-trained model and the fine-tuning, which is, I think, right here. So those are the two networks that we have to discuss. We will discuss those this afternoon, and I hope very positively that I can show you this one, the PyTorch way, which also has some other things there. There are particular for PyTorch, and at least a first introduction to the recurrent neural networks. So I start with one, trying to see what happens when you are dealing with a time series. This predicting the climate, this kind of network, from values from a sensor, a set of values. So we are trying to predicting the next 24 hours in the future. So what you will be doing if you are thinking about a dense neural network? What will happen if you try to use a convolution? In that case, it's just 1D convolution. And after that, there will be a justification for moving into those recurrent neural networks when you are injecting inputs, outputs as inputs into the network. So they operate very particular, and they have their own applications. And those applications are really close to science, and so like sounds, signals, things like that. So I don't want to leave it, at least explaining a little bit the LSTM at least once. So we close for this morning, and we continue for the two other networks this afternoon. We'll start at this point. We will be starting this point at 2 o'clock. So we have like 2-3 notebooks for the afternoon. Thank you very much. So we have 31 people who survived to this point. I'm very happy with that. Plus around 8 here, so we have around 40. This is a big success because someone was forecasting that I will end up with 3 people. So I am 1 order of magnitude better. So that is something that pleases me very much. But please fill those. I would like to see if for example, the next time I would like to see, or send me messages if you feel comfortable with that, send me messages if you prefer something like higher level or more, or one particular, not three different frameworks, focus on just one particular framework, or just doing a workshop just in convolutional neural networks, or how you will see this moving forward in the future. That will help me to try to figure it out. What can, if, for example, Python was a handicap for you, that is another thing that I don't know. How many people is? I assume that Python is like part of the digital alphabetization, or you should have as a scientist. But I don't know. Is some people work with R, and that's perfectly fine. So thank you very much. We will see. We will continue this afternoon. So please remember to fill the form. See this form. Right here. So fill this form and tell us what you think. It will help me a lot in future notebook and in future workshops that I could offer. Let's see. It's still warming this screen. Okay. In the meantime, let's see. Don't forget that you can take all this data with you, the entire folder. Try to use close. It's much better. Those are 5 GB of data, and I will actually clean that a little bit right now, just in case that you want to use it. I will do some cleaning there. The output. Okay. That's better. It's 5 gigabytes, so you can take that and almost 300 files, so it's still manageable, but it's better if you do it this way using Globus. The transfer will be parallelized. It will be, you will have checking that the files on your side are identical to the files. Is still not projecting this thing? Oh, okay. No, that's okay. Okay. So yes, you can copy all the data. The data will be for a few weeks there before I remove it. So you can take that. All that you need is having MXNet or PyTorch or TensorFlow, and in the title of the notebook, when they require something like one of those, I put those in parentheses. When the notebook doesn't require anything other than NumPy or scikit-learn or more basic Python packages, you don't see anything there, parentheses. That is basically the idea with those notebooks. So we will recapitulate this, we will move forward here, and we will see back our problem. Okay, training a convolutional neural network when we have a small amount of data. Is that a question? Oh yes, if you want them to be converted into into a PDF, I think there is one option here to export those to PDF. I never did it before, and you probably need that. What I imagine it will happen is that it goes into something called pandoc. So you need pandoc on your computer that will be translated into LaTeX. So you need LaTeX to compile that, or PDF LaTeX to get the PDF. So not super sure. For sure, in the cluster will not happen because we don't have LaTeX there. So that's the reason why I have to disable LaTeX on some of the notebooks. But on your side, if you have all those packages, yes, you can convert those into PDFs or HTML files if you want. Yeah, but not directly on the cluster. If you try to do it here, it will most likely fail. So when we have a small data set, by small I mean something like in the order of a few thousand images, which could be a lot for some practical applications still. There are a few things that you can do. So basically 3 things that we will be exploring here. One is what is called data augmentation. So it means to apply some at the input level, applying some transformations to the data, so you can offer a larger variety of apparently different inputs to the neural network. So we will see that increases the performance of the network. And if you have enough resources, by that, if you have GPUs, you can go into the other 2 options, which are taking the biggest portion of a neural network that has been pre-trained and only train the last part of the network. So that's one option, but still it's an option that requires a lot of GPU, so some computational power for that, or still work with an important portion of a model and tune the final layers of the final convolutions, and after that also train the final dense layers before it enters to the classifier. So the last two options are computationally intense. So you need a machine that is capable of doing that efficiently, because typically what you do is to take a model, those pre-trained models, they have in the order of between 10 to 100 million parameters. So even if you are not changing them, still it takes a while you traverse your data through those large models. So that is one thing that we will see here. So this notebook, for sure, we need GPUs as well for the next one. So that's what we will be exploring here. So what I will be doing is executing the first part here, and I will be up to the point where I will be training this. So in the meantime, while it's processing this, I talk. Oh, I forgot. Keep that. Probably will start it all of it. I will probably have to execute at least for the test. Start training. Okay, to this point, and eventually the history and the plot. And the rubbish. And this. Okay, up to this point. So let's recapitulate what we did. Oh, what is this? Oh, this is what this is my fault. Apparently, yes. Eventually, this could happen. Oh, somebody else is running this. So let's see how I can tweak this a little bit. this will cure that. This is one. This is the dog. Now, oh, yes, yes, thank you. Thank you for that. So here. So here we have the original network. And we compile the network. And all that we are doing here, we are still not in the augmentation process. All that we are doing is getting whatever the size of the image originally is, return something that is 180 times 180. And we will create like those tiny machines, like data feeders or data pushers that will produce batches of size 32. That is what we are doing here for the training, validation, and test. So that will start producing those samples in batches. So that is what we have here. Okay. So those are, this is the typical size of the multidimensional array that we get when we request one of those batches of data and labels. The shape of those is 32, the size of the batch. We have 180. This is one of the dimensions of the picture. The another 180, and the final axis will contain the RGB components of the image. And here what we have is just 32 numbers that will be correlated to the numbers, to the labels associated to them. So if it's a cat or if it's a dog, that is the content of that. And we will be using a callback here, and we will provide this callback to the model. So every single time that we move an epoch, we will be storing the weights, the best weights to that point. This one runs quickly. So for this one, you can still do it with CPUs with too much trouble. It will be slower, but not painfully slow. So it's just a matter of waiting a little while. Now, I think we can see as to here. So what is the idea with the data augmentation? We will take the image and we will introduce some rotations on horizontal. So you see the cats could be flipped horizontally and they will still look like a cat. So that is something that is not changing for our perspective and our ability to identify those objects. And after that, we are eventually also adding some rotation with some random number and assuming. So we are going closer to the image or zooming out. So that will help us also to create a variety of variations of the data. So at the end, at least with what this is what we typically get. So for the training looks fine. At some point it saturates, But what the important curve is the continuous curve here, the blue one, that shows that for the validation data, we are stuck around 70% accuracy. And what we will be like to do is to first try to avoid this overfitting, and second, of course, trying to move this curve up there. And so now we will apply the first trick, the augmentation. So we create this sequence of layers that will operate like that, and we will insert those as another layer in our model. So here, this is just an example of a few of those cats. They just took a random image of one of them, and I applied the transformation. So you see some of those are the rotations, some scaling. So you see the cat a little further away, rotated or scaled. So that is what we are doing. So notice that we are putting that augmentation layer on the very top of our model. So this is the input. So the inputs will be injected here in our data augmentation function. After that, those will be injected in the rescaling, also divided by 255. So we will get real numbers here, and here is where we are start with the traditional convolutions, plus max poolings from whatever was the object behind it. So this is just a traditional stack or pile of layers, and at the very end we have, of course, a flattening of the network, a 0.5 dropout, and the final dense layer with just one number, because we only need one number. So the probability of being a cat or a non-cat, which is a dog. So for that, the only that we need is like we use for a perceptron, just a sigmoid will help us to identify the two classes directly. So we don't need a softmax. And that's what we are doing here. So so now we have this with the callbacks. This one, this is still something relatively fast. The only thing is that now we jump in the number of epochs. So here is the reason why it will take a while to get. And in the meantime, even if I cannot execute it here right now until we get all those epochs complete, the idea of taking a pre-trained model and just modifying the very last part of that. So we trust that the model that has been trained with, in particular, a more complex problem, or at least a more richer case, that could be the ImageNet. So in the ImageNet, they have animals, all sort of animals. I think they have probably human objects, so cars probably, I'm not really sure. But they have a variety of classes. They have 1,000 classes in ImageNet. So we hope all those transformations, all those kernels are pretty much like Lego blocks that work well, trying to capture the features. And the only thing that we need to do is to replace the final dense layer, which is taking all those features processed already, and do the classification that we need for the cats and the dogs. So we will be taking advantage of all that has been done with that network. It's just changing the final one. So how we do that? So we can take a network. This is one of those networks that Keras has available. And we will not be, well, at this point, it's just because yes, probably this is one of those things that I changed. So I have to remove the wakes, so put wakes, otherwise it will try to download those. If you put, I think, true, it will, or you put string there, it will try to download the wakes that are also over internet. That will fail. So what I did was to first put the wakes in none, so an untrained network, build an untrained network, and just by hand taking the file with the wakes and injecting that and loading the wakes separately. So that this is just these two lines here is just the fact that we don't have internet access, and that's the trick that we use to skip that part. So when it's finished, we get this, we can see this. Those networks are complex. I think this one, if I'm not wrong, they have like 14 million parameters. So we will be using that. We will not be training those 14 million parameters. We just freeze those, and just the very last part, it will be modified. So here, let's see, put that in here. What's the name of this base? Okay. Okay, this is the VGG 16. So, okay, so it means that I got it. So that is 3. Okay, well, this one was the first one. And after the, okay, this one. So this one complete, it's now complete. So we got something in 82% on the validation data. So, okay, not bad. So now we took those wakes, we create this cone base, so the portion of this model. What we are doing here is saying, please do not include the final part of that model. So the very last dense layers. So keep everything else. Give me the weights. So use these weights here. So fill this. So this one will include the input. It's a convolution plus max pooling. Convolution plus max pooling. So the way this works is slightly different. So a set of convolutions in cascade, and only after a few they go into the max poolings. So you see here 14,000, almost 15 million parameters to train. So here, what I'm doing is taking what I'm doing here. Okay, so yeah, I'm using the training data set, the validation data set, and I injecting those into the function. Okay, so that is okay. And this is what I get. So here, okay, so here I'm defining just the part of the dense part, so the classifier. This is what I'm doing here. Yes.
Like why you have used like from the epochs history and epoch epoch reduction factor? Why are you reducing the epochs?
What?
Epochs the history.
This one.
Yeah.
Okay, this one was something that I put on the very top. I was trying to. I have a hope that I could make this here something that I could run with a CPU in a reasonable amount of time. So I was trying to see if by reducing a little bit the number of epochs, in case that I don't have access to a GPU or too many people were using the GPU and I was forced to use the CPU, that I could still be able to present this notebook in a reasonable long time, because I know that this part is very expensive. So that was the trick. So here I am checking if I have access to the GPU, and if I have access, it's okay. The epoch factor is 1, so I will keep the original version. If I am constrained on that, I will just keep just 25% of the original value. So they're very tiny. It will not be good, let's say, in the curve at the end, but at least I can, and I put this in general so I could use it everywhere in the notebook. But the fact is that it will. The best option is always to use the GPU to get this in a reasonable amount of time. So, okay, we already did this. So probably we can convert that. Okay. So now we raise the bar with this. So now using that thing goes significantly higher. If you compare this is around 97 for the validation using this. So we got, 97. Just with that, if you compare that value here with the other curve here, this one was around 70. So there is a significant advantage on changing from just training your own network and reusing something, of course, with 14 million parameters, so much richer, already trained. And so someone else took the work to train this network. This is an expensive work, but after you have it, you can reuse it and get a very good classifier for a small amount of data. So that is the whole point of doing this. So 97. So we move the bar, we're in 97, which is really good to considering the little amount of data that we have. Now, what we will be doing here is using this one. Again, so we have the BGG 16 and not including the top, not including the last part. We'll put in those weights here. And just disabling the modifications to those values. So that will be slightly. So if we take that, this is the number of wakes before freezing. Okay, if we freeze everything, it will be, of course, no parameters. What I'm doing here, let's train them all through complex. Let me show this. So now we take that. Now we put the data augmentation on top of that. Now we are taking this section here, that is the frozen part, yeah, with the data augmentation. So is this data will be changed, will be entered here in the input, will be augmented, and they will enter in this block that is not trained. We are not training this part. This is just black box, a function that takes the take the inputs, and will produce something that we take here, move, flatten, and move into the ends, and finish. So put the callbacks there, and this time we'll bring 50. And this one is, I think, the final one. Yes. So now we are combining the fact that we are pre-training and the fact that we are now adding the augmentation to get, I think, something 98 or something. We'll see what we can. We are around 95. Really quickly, we're 95, 96. So this one will go higher. And now we move into this other way of doing, another expensive way using a pre-trained model. So I think I already execute this before. Here I put it by hand here. So this is the VGG16. So you see two convolutions, one max pooling, two convolution, one max pooling. Now sequence of 3 convolution and max pooling. So that's what we will be using here as a template for this one. See, this one is, it will take a while. So now we will say the com base, this base. So all those BGG16, we first enable the training, and after we freeze a certain number of layers. So we are freezing all the layers except the last 4. So we will have still some ability to change some of the last convolutions of that network. So 4, that means that we are keeping everything except the last 3 convolutions and the max pooling. All this section is unfreeze. Everything else is still frozen. So that is the answer. So in order of complexity, in order of computational cost, this one will be the next, and after this one will be, well, training the whole thing from scratch. Okay, so we will see if we get this one. But I can still try to execute this. So let's recapitulate, because it will take a while to complete this. I already marked those for execution. So 4 cases, we train here 4 networks. First one was, let's say, the vanilla one, the network of the simple network, no augmentation. That was our baseline. So the simple network. It was this one. So simple layer, input, the rescaling, of course, moving that, the figures in the pair. What we are not rotating, we are not zooming, we are doing nothing like that. It's just the figure 80, 180, 180, nothing else. So we trained this, and we got, after training here, after 30 epochs, we got this curve. And this curve tells us, okay, forget about the training accuracy. that's a lie. So the real value is the 0.7 that we see here, 0.7. That's what we can trust, and we can confirm that with the test data. After that, what we did was adding the augmentation. This is the whole point of the augmentation. There are several functions in the Keras documentation that do more things like this. You can flip vertical, cut, inverted. Well, it's probably not what we expect. And the network to be, except if you want to be able to capture the cut, no matter if it's the image is inverted. And those are examples, and we took that network, and here we added. So the difference will be this with respect to the previous one, and the fact that we now are having a dropout at the very end. So after the flattening, we put a dropout. That's the only thing. And now we don't. I forgot to put the plot of this one. Great. So I'm missing the plot here. So now with all the convolutions frozen, like a big function that is like black box, no changes to those parameters. We stack that with a final classifier, and we got this one. So we raised this to 97%. And the final thing that we did was to take the original network, the VGG16, allow that to be trained. So we enable the network to be trainable. And at some point, we freeze some of the layers. So with the freezing of the layers. Yeah, here. So we are freezing all the layers except the last 4. And that is what we are training here. I don't know if we finish. We're close to finishing this one. And we should see the accuracy, but at this point is 99.7. So we are almost, well, that's for the training. For the validation, 97 points. So we raised that to 98%. Which is good, considering that we have just 2,000 images. So that is the kind of thing that we can do if we are in this situation. Just a few, 5 more, and I think we can move. There are similar, I just picked this one from TensorFlow, but there are similar operations like this in the other frameworks. So those techniques are widely used. By the way, this is not particularly big for today's standards. So there are others. You go to, I think, where are these? You see here this one. You see here. I think they have the tables that you can use. All of them. So here, so they show you here, I think it's right here, where you see networks that were trained with ImageNet. So with this large collection, I think the collection is 13 or 18 million images. So it's a very, very large collection of data, of images, and you can take one of those. I was expecting, I don't know if it's in TensorFlow or is in the in PyTorch, but they have a nice table when they say the number of parameters on those networks. But I think you can check here. So if you go here on, let's see, I'll put you the reference, but not the size of that. So other networks that you can use for that. yeah, I got, yeah. With the validation, I got 98. When I put that into the test data, I got 97.3. So that is okay. So those are the three things that we can do. And I think we can move on into another part here that I think I can move that. And so I can close this thing and I can go into this final example for the recurrent neural networks. This is a completely different thing. No more images. Yeah, let's see if I can clean this data here. Still TensorFlow. So we will talk about recurrent neural networks. I am mentioning where I'm taking this. This is from the book from Deep Learning with Python, second edition. And so it's a modified version of what is there. So here I am taking a table of data from one place in Germany where they captured during many years 14 parameters like the temperature, the pressure, the direction of the wing, things like that. So 14 different parameters, climate, weather related. And from that collection, we are taking just a small section of that, 2009 to 2016. Those are in one zip file here, that is this one. So I don't have internet access here, so I have to download the data by myself and put it there. So what I'm doing is extracting the data without actually putting the file in the file system and just gathering the data as a text file. From there, I'm doing what is typically done with those kind of things is that I am splitting the lines. I can do this, or I can change if you put read lines, it will produce the same thing. But here in Python 3, it returns a byte, so I need to decode that in UTF-8. There are some subtleties here that I will not go into. But the point is, at the end of this, I'm getting a string, a long string. I am splitting that string with the new lines, and for each line, I am splitting that with commas. We need to be careful if you're not able to see those, because sometimes you have like in quotation marks the names of things with commas, and it will destroy this cheap way of splitting files. So you need to use something more sophisticated. And there are some libraries that are capable of splitting this, even if we have quotes with commas in the middle that could complicate things here. But this is not the case. What we have is a long line. So so I probably can execute this and show you one line. It's not that bad. So when I execute this, if I see one of those lines, say lines, so this is what we get. So some timestamp, some values, and I think the values correspond to this. So we have pressure, temperature, velocity, wind, other pressures here in millibars. A bunch of data, 14 columns here. And we would like to predict the weather one day in advance using the data from the past. That is the objective. So we are making a weather model thing with this. What I'm doing is separating this data in this way. What I would like is to predict the temperature in the future. So I will be taking that. Those will be my objective, my objective function, something that I will separate. And I will keep all the data except, I think, the first column. I think I'm keeping the first column. Yeah, I am removing the first column. So I'm keeping everything else. So I have one vector that contains the temperatures and another array that contains everything except the first column. But the first column is the date and time. So I know that those are in sequence, but I will be skipping the date and the time. Now, this is how this data, okay, now it's collecting all that. And this is how this looks like. So we have, if you see here, this is temperature. So we are here seeing one summer. And we start in a winter. So probably this start in January. So we are deep in the winter in Germany, in Jena. Winter here. So you see the peaks, you see the seasonality of the temperature. So that's okay. And that will give us some information there. And now what we are doing is taking just the first 1,440 data points. I think the data is separated by 6 hours or 50 minutes. I don't remember exactly. So you see here the day and the night. The day and the night in one place during the winter. So temperature were -10, -20, so a typical German day in the winter. And this was long ago, I think. Well, not so long ago, but it's 2009. So well, it's still things have changed over the years. So that's what we have here. Yeah. So this is the amount of data that we have. So we will need to prepare the data. The idea is that we will be collecting windows of data with separations of 6 hours, I think, and that was what is happening there. And the idea is that with the previous values, we try to predict the temperature 24 hours in the future. For that, we are selecting the all pass 2009, probably 2015 for training. We will be selecting a portion closer to the present for validation and another portion of that for testing. So closer to the present. We also have something here is if you see those values here, some of them are really large, some of them are moderate, so they have a completely different scales. So we need to rescale all that. So what we are doing there and is with NumPy is we are taking the values here on the axis 0. So for every single column, for all the rows and for every single column, we are taking the mean and we are storing that. So this is a NumPy operation. So we're storing that, the mean. So the mean will be a collection of 14 values of the mean. So and the standard deviation. And we will be correcting the values, rescaling the values with the mean and dividing those by the standard deviation. So we will be getting all of them under the same ranges, so normalizing the data. That's what we are doing here. You can see how those mean looks like. So those are the average of that. So we use that for scaling, and we are storing that because at some point, the data that we receive as input, we will have to do it the same treatment that we are doing here. And if we like to record, for example, the temperature, we need to undo this normalization. So STD here, those are the values. So we need those both in the input. When we get the data, we need to rescale it, normalize the data that we will offer. And at the in the output, if we want to recover the temperature back again, we need to go to undo this operation somehow. So now, what I'm doing here. Let's see. Oh, what? Oh. What I did wrong. This. I don't know why, but it's failing on the GPU, so it will be running slow. Let's see how far I can go using just the CPU. Those are heavy, so that these not networks take time to train. Let me see. So here I am just making an example here. What I would like to expect is that I will be offering like a set of values from. No, it's because I am using my own. I don't think so. The data is not in a temporary folder. That was my mistake before. I don't think so. And I using my own folder with deep learning, so it's not the share. But it's still getting those crashes, and I don't understand. All is working. It's working now. I will, in any case, I will kill this one. I will keep just this one. Now, okay. Let's see. But this is still running. Oh no, it's training this one. So, okay. So, so what we did here is selecting the samples. So the samples will have the batch size, which is 256, like collections of different sections in time. They don't have any order in particular. The point is, from those we have 120 values, so they are in sequence in time, with separations I think is 6 hours. So we have like 5 days on those there. So 5 days. So we have 5 days of data. For those 5 days of data with values collected with 6 hours of separation, we have 14 values. And the 14 values are those temperatures, pressures, winds, directions, velocities, all that that are here. So here are the features that will go the input in the network. Here I have all the times. So this is like a matrix. If you think those are, they have the direction of time is in the 120, and the features of that is in the 14. And we have here 256 batches or a batch of those samples here. And the targets are 256 values of temperature that we would like to predict that we get from the future. So those are the collections that we have. So what we are doing is, for the sampling here, for the targets, is moving from the final position of the time for the sample 24 hours in the future and getting that value. That is what we are doing. So the first thing is saying, okay, let's start with a common sense model for this, not using neural networks. It will be that the temperature tomorrow at this time, it will be exactly the same temperature that we have right now. That is like a naive model that we will use to see how far we are from that assumption. If we can do better than that, it's because the network is doing something. The idea with that, okay, so the only thing that we are doing here is taking the predictions will be that the last value of temperature from my samples, for all the value that we have, we will be collecting the final value, so the last value of the second column. And the second column, if you see there on the top of this, second column of this, forget it, we remove the day of time. So the second column is the temperature. So the temperature at 3:12 tomorrow, it will be the same temperature that we have right now. So that is the naive model. And with that naive model, if you inspect all the values, you get a deviation of 2.4 degrees. So that is the mean that we get. So we should be able to do better than that, to predict that better than just 2.4 degrees. So for that, we will start with the first thing that we learned, that were dense neural networks. So it means that we will be taking for all the times those 14 and stretch them to stack them like in a big vector and use them for training the network to see what we get. So you see here, the way we have is that we take this input for the values, we flatten that, we insert that into a dense layer of 16 neurons, another dense layer with just one neuron. We'll collect the data from the 16, and with that, that will be the output. That will be the output scale. So we need to take that and revert. So. Oh, it is right here. So let's see. So it's right here. We have, when we prepare the data. When we prepare the data here, when we read the data, we have this number of lines. So we have the 14 columns, all those. From those, we are collecting in jumps of 6 hours. I don't remember exactly what is the finest grain in the data, but we are collecting 100 in sections of 120 values with separations of 6 hours. So we are collecting 5 days of data. And for them, is the whole data from 2009 to 2016. We can take, okay, those values and store also the prediction of the future value that will be the value 6 hours, 24 hours after that. So the way you construct that in the data is right here. Right here. So we are taking, the sample rate is 6. So we are taking every 6 points. So we are collecting one. So we are collecting batches or sections of 120 values. So that means that if each value is separated 6 hours from the next one, we have 5 days of data. So with the 14 columns, so that value times 14, and the future value, the prediction, the final value that we would like to get from the function, it will be that 24 hours in the future. So that's it. So the initial point, the sample rate times the length of the function, the 120, plus 24 hours -1 because we start the indices from 0, so that will give us 24 hours in the future. That's how we get the future. From the data that we already know, you already have all the data from 2009, 2016. So in 2010, we already have what was the temperature in, say, in January 2010, in one specific day of January 2010, we know what was the temperature the next day. And so we are making a column with the date in the future. And we are separating also on a section of the data for the training, which is the old data. So from 2009 to 2014, maybe, that will be the training data. From 2014 to 2015 will be the test data. So we already know that it's in the past, but we will not be using that for the training. And we will have a test data that will be between 2015 to 2016. So it's also in the past. So it's something that we will use just for tests. So we always are working in the past. And we are trying to make a model that if we inject data from the past, but more recent, we are getting it right. That's the idea. So, so everything is in the past. Everything is already something that was collected. And so, okay, so this one is the common sense model. So predicting that this line, this is the crucial line. So then okay, you got it? Okay. So the predictions for tomorrow, it will be the temperature that we have today, times the standard deviation plus the mean. So it will be recovering the value in, I think it's what they are German, so this centigrade. So I think it's centigrade. What is this? Yes. So it's in degrees in Celsius. Celsius. Yeah. That is the thing. So now we should be doing better than that. We should be having a much better figures than those errors. So what are we doing? The first thing is trying a dense layer. At the end is just one neuron. The whole work, it will be a matrix multiplication that is happening here with a 16 layer, with a layer, hidden layer with 16 values, and a ReLU. So that is what we would like to use first. So we got a difference that is pretty much the same. So our neural network is as good as our prediction of tomorrow will be like today. That is, well, what is so slow? Okay. There is something happening in the cluster. I don't know what is so slow. Even to plot something is slow. Well, we will see the image. I don't know when exactly, but we will get the image at some point. So the next thing that we can try is then the next thing that we learned from this workshop, and the word the convolutional neural networks. Now we don't have an image, but we have something where we can apply 1D convolution. So the 1D convolution will be taking a kernel, which is a vector in this case, and we will be moving that vector in tiny windows. So we will see a little bit of what was the values 6 hours ago and 12 hours ago, and collecting that and getting the value. So that is what we're doing here. So this will be like the equivalent of convolution. It's a convolution in one direction, so it's a vector. We are using that. 8 channels, so we will get 8 different versions of that. After that, we are taking a max pooling, so we are taking 2 values. We are doing what we learned to do with a convolutional neural network. 2 layers here, convolution max pooling, 1D. The last part, it will be a dense layer here, and that's the value. So that is our next, okay, I think already trained that. And we got even worse. So that definitely is not a good idea. And the reason that we expect for that is that when you are doing this, you are assuming that the temperatures or the climate is translational invariant somehow, like we think for images. And while it's not, the temperature tomorrow, you shift 6 hours, so you want afternoon, and afternoons are, I don't have the same temperature as mornings, and even worse, the temperature during the night have nothing to do with what was the temperature. So it's not the same temperature that we have in the afternoon. So that translational invariance happens with images, but it's not happening at all with temperatures, pressure, all those values. So that will not work. So that will call us, and at least to reach to this point, to the first recurrent neural network. The idea of a recurrent neural network, if I am able to draw here something, it's nice, it's beautiful, it's simple. It's taking the values. So we need, we have those 14 values here. All those 14 values. We will be using for them a weight. So we will be doing like a matrix multiplication of those weights times the inputs here. And here we will be putting, imagine that we are putting just zeros at the very beginning. So X, Y, so with Einstein convention, it will be something like this. So we assume that there is a sum there. We take this, here we have, imagine another weights that I will call use, that probably is fine, use I, initially with those Y's, right? After doing this operation, whatever was this output here will be replaced here. So the next time that we enter here with the next time, we will use now these other values that will be from the past. So this will be the output from the past, re-injected as part of the input for the next cycle. So this is something that has like internal loops that originally are zero and are being re-injected in inputs here. That is the reason for the recurrence. And what we are taking is the 14 values here, going here. So we have this set of weights, this set of weights. So there are 2 matrices of weights. And for the entire 120 hours, so we will be taking the 14 from, say, the original 5 days ago. We will start with zeros here. We compute this. 6 hours later, we take the output here and the values here. We inject those. So 12 hours from the beginning, we will be injecting those, doing the same operation again, until we get everything. This, the outputs here at the end will be projected, I think, in a dense layer. Yes, and a final dense layer here, which is what will give us the final result. So that is the idea of this long, short-term memory-based model, which is the first recurrent network that we have. I think I got it. What was the final value? Was still, well, it's still better than that. We got compared this value here for the test, 2.58. Of course, it was much better than the convolutional. It's better than this one, which is also better than the naive method. So it's better than just saying that tomorrow is like today. So now we have a network that is capable of doing a little bit better. So that is the, well, that is the central point of using these recurrent networks. Here, I think this is just an example of what is happening just with NumPy. When I explain, I think that I'm using exactly the same. Oh, let me see if I got the image here or not. This is still doing something. Something happening with this. Just on the final. Great. Okay. In the meantime, so at some point it will execute this. This one, this one, and this one. So I told you there is a matrix here, W's here, the X's here. This is one of the weights, a section of the weights. The other section is what here they call U's. So at the very beginning, they put the state, what is this path that we will be using at zeros. So we put here zeros originally, we compute, and we are putting here random numbers for this. So we are filling the W matrix here with random values, the U matrix with random values. We are computing the dot product. Where is the dot product? Yes, here. The dot products of the W's with the input and the dot products of the U with the state, originally with zeros, plus the bias. So we also, I forgot the bias, plus the bias. So this one has a bias here. So it will be this matrix plus one, the number of tunable parameters in our system, envelop that in a hyperbolic tangent. So it will be like a logistic function on top of that, or something like that. And that is the output. And we say now the state of the system is this output. And we will use that. So that's what I told you, that after you put this here, and you envelop this with a sigmoid, this is what you put here again to be prepared to receive the next, the data from the next 6 hours. There. So, yeah, that is what is doing that. So here we are preparing another one. Let me see. Okay. Okay, so slow. Let me see how far I can go with this. Okay, so now we will be preparing here, this another layer here, here. Yeah, we can do this same trick and use this like a tiny little block to put more of those ideas in place, so more of those recursive. So we will be making like something like that, assuming that this is, I will be representing this. Okay, so we have the input here. The input here will be 120 values with 14 futures elements here. So we have 14 here. This is my table of inputs. Great. So I will be entering those into this recursive network. So I will symbolize that with this. So it will be taking this value, entering here, doing this operation. So here internally we have a W, a U matrix, a bias. It will enter here. It will process this section here in the recursive way. And after that, we can take that and reinject that into another one, another one of those. So that is what is happening here. If you see box 30, the input 30 here, that it was executed or not? Oh, it's executed before. I need to re-execute that. So here we have an ARNI, a recursive here, putting that with the inputs, and now stacking that another recursive from the output from the previous. So it's the same. Is the same. Those are heavy. So unfortunately, for some reason, it's failing to me when I use GPU. So I probably will not be able to go too far from there, because this took me like 40 minutes running with GPUs. So it will take hours to run this with CPUs. So probably what I would like to do is, let's see if I can. This one failed when I don't remember. So after that, all that we are using is variations of that, adding other different layers like that. But unfortunately, I don't think that I will be able. Those finals are really, really heavy. And you will see that we get really good results when we use stacks or recursive. And this is the solution. And unfortunately, I don't think that we'll be able to run those. For many cases that has some practical interest in science, unfortunately, that's like sound, electrocardiograms, so things that follow the pattern of the time, follow some time series problems. This is what you use. There are some more advanced variations of that. So you see those here. Probably what I can do is to show you in the collection that I have here, those in the map while this is being executed. All those here. So those are convolutions where they are, the recursive, the recurrent here. So those blues here. So you see here stacks. Or this one was what we were using, the long short-term memory. That was our recursion. What I was planning to show you, the more complex one, is this gated recurrent. So those here with blues are those recurrent neural networks, where the LSTM and the GRU are just particular cases of those. Unfortunately, this will not work. It will be without GPUs. It's a pain, and for some reason I don't know exactly why. Because I test all those notebooks. Just today they are failing with the GPUs. So with that, I probably will close here. Will entertain questions from you, general questions from everything, including Python, including machine learning, whatever, what you want for me to tell you, to see. Just tell me. Otherwise, we will be closing at this point.
So I have a question.
Okay.
So I have a question, like for the time series that were showing us. One is so you are using the CNN for the one-dimensional data, is it convolutional one?
Yes, that,
1D. So I was considering like, how are you going to use the kernel for the 1D for 1D?
oh, it will be something like this. It will be something, imagine that you have like the pressures, you are typing the pressure. So the pressure, you have the table like this. So this one, let's say at time 0, it will be the pressure, the pressure, the pressure, the pressure, 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 something like that. Imagine that, so 0 hours, something value here, a value here, and now you will be doing a convolution with an array of 3. So those are values that you will train. You will be multiplying this by this one, this one, this one, this one, this one, and adding the sum, and this will be your output. It's exactly the same you expected. So all those will be the multiplication of those 3 with the corresponding pressures, summing, it will be here. So now we shift. So now you move and to the next section here, and the value here, the values here is the same kernel. So they will go here and they will produce this value here. So at the end, if you have, let's say, 120 here, and the end with this, you will be losing 1 block here at the very beginning, 1 block at the end. So this one will be shorter by 2 indices from the pressure. So those will be like pressures convoluted, that will be 1/18 of them. So that is exactly what you would expect to do with the convolution. And if you after that, and that's what we did there, was to do a max pooling. So that means that from my pressure, I was taking something that was like this, taking all those 2 values and storing here the maximum of them. So the maximum go here. You make a stripe, typically you make a stripe, so you don't use those anymore. So you have 2 new values here, let's say square here, all those things. You compute the maximum here and you store it here. So those 2. So now you have here originally pressures 120 here, so we have 120 here. And when we convert those with the convolution, we got the pressures prime. It will be 118 of those. And when we apply the max pooling, we will reduce that to 63, 60, 62, no.
56. Sorry.
No, 59.
59.
59. And we are doing that also for all the other columns, the velocities, the wind velocities, all that. We will be compacting all that. So the assumption of that is that there is some invariance, time invariance, that which makes no sense, and that's why it's even worse that they assume that tomorrow is like today. So you will get the pressure now, the pressure in let's say in the morning, in the afternoon, during the night. Well, no, there is no such translational variance with the time. So, okay. And more questions?
Further up, so.
Further up.
There's one more about LSTM above that.
No, for videos, you continue to think about convolutions. Now so for sound or for, let's say, for signals, which is something that have a lot of scientific applications. We use our, so convolutions will be for things like images, things with translational invariance. For video, in this case, the convolution will be 3D. So it will be like a cube of values. So our weights will be cubes of values. So we will have a weights here that will be taking at least, yes, the fact that 1 millisecond in the future is still something that is similar to 1 millisecond or 1 frame before. But in the long term, you can probably combine those with recurrent because they also have the time. So it probably will be a combination of that. But if you see that from the visual point of view, they fit better for convolutions. For time series, you can think about them more with recurrent. You can pre-convert those with eventually with a Fourier transform. So you work with them in the frequency domain, maybe, but still you can do things like that. But yes, and okay, because yeah, so this is the idea. If you want, let's say, something like a formal consulting thing, you can just open a ticket on the system or here. So if you want to be formal, you can just here, the same place where you can request an account on the cluster. So you go here, helpdesk.hpc.wvu, and you can send a request if you want to discuss something related to research and the possibilities that your research can be accelerated to improve or something using the cluster, using our HPC resources. So that's one thing. If you want, you have my email. You can also send me a message if you feel comfortable doing that. Also, if you want a particular software you want to install on the cluster and that software is possible to install in the cluster, this is something that also I can help you with. Or sometimes updating some things or teaching you if you want, for example, you know a software and you want to know how to build, for example, a Conda environment for a particular software. We have Conda there on the cluster, so you can build your own Conda environments for things that you want. Sometimes the solutions will be singularity containers, that's another option, or software installed locally. So all those things, you can contact me if you want to discuss the options that you can eventually have for that, for running your jobs or improving the way you work, or how to submit jobs, or how to scale your execution in such a way that you get your papers, more papers, better papers. And so you will be happy, your PI will be happy, university will be proud. So all those things help us. Okay, so that's it. Temperature. When you work on the temperature, where the other humidity, wind speed, basically no. No, they were accounted. They were accounted in the prediction. Let's see here. Let's see. Oh, here. So all those were, let's say, if you see here, when I collect, let me see if I can get some. One line will have all the data. When I was building those sections, in some point, I have the shape of the array. Yes, right here. So you see here, I have the trained data set, and I asking a sample. Give me one sample, give me one the targets, and the sample will be 256 120. So this is the time. So this is the batch axis. This is the time axis, if you want, and this is the feature axis, if you want. So all the 14 columns for all 120 times that are separated 6 hours one from the next one, all those are accounted. In the dense layer, we took all those and we flattened those. So we got 120 times 14 long lists of numbers, and we hope that network to work with those numbers somehow. And here in the targets, what we have is a long list of what was the temperature the next day when the window was like this. When the window of temperatures and the other 14 variables were like this at some point in the past, the next day, this is what happened. So that is the idea. So here is another way of clarifying what we did. So if you see here the samples, we are taking all of them. The last value, so the last value, so the final value here, that's the -1, and the column 1 was the temperature. So if this, for this model, we are ignoring everything, pressures, velocities of the wind, all that. We say, forget about all the 13 variables. All that matters is that tomorrow will be like today in terms of temperature. And after we scale by the standard deviation too, because this is a scale value, so we are de-scaling that, denormalizing to get the predictions. And the final one, the error or the variation of that was 2.6. We inject that into a dense neural network, which is also taking that. If you see here, it's probably because this model, I never print the summary, but the summary will tell you that we are actually taking all those inputs here, so into consideration. So, but that's a bad idea. So taking all those without any, not preserving the cycle of the time, it will not help us. And this one is the first one that where we are really using the recursiveness, which is a nice trick to use. And this one, for example, is just mathematical expression of what we are doing. But yes, the equation will be u times the input plus w times the input plus u times the previous state at the beginning 0 plus the bias. And we are using that with all the 14 columns for all the times until you get the output that will be entering the next one. In the next recursive, because what we will be doing after that is start stacking those recursive networks. So they will be doing transformations to the data in layers. Okay. Anything else? Anyone? Something? Yes, the data. Well, the data is ordered when we receive it here, but the data is not ordered when we train. So here, when you receive this, the data is in a sequence. So from, let's say, January 1st, 2009, and every single date. So well, we try. See, this is. If I execute this one, I can show you here. Let's see. Well, I can put probably like this. The first one. So this is probably 13 lines. So 13 lines. So you see the dates here, which is this. and the time here is right here. So January 1st, 2009, at midnight 10 minutes. After that, 20 minutes, 30 minutes. So the data was collected every 10 minutes here. We are making jumps on that, so we are collecting the data every 6 hours. But when we are moving into the network with the sampler where the data, those here, when we build those will be sending out random sections of 5 days of data from different years in no particular sequence. So we will send something from 2010 in one particular day of that year, 5 days, and that's what it will be injected in the network. The next time will be something in 2013, in August, and it will be one of those days, another second. So we will be skipping all the time, just Windows 5 days. The idea is with 5 days of data, can I predict what will be the temperature tomorrow? That is the whole point. So I am offering jumps, tiny windows randomly. So that is the whole point here. We are shuffling that. That's why we have a true here. So there is not a sequence. There we are not a star or offering that from 2009, 2010, So let's say, and also the time is still relatively short, at least for the climate change. So still in those years, I don't know if the temperature globally have increased more than 1 degree. I don't think so. I don't know exactly what is how the temperatures globally are changing. You can inspect a little bit here that they are going up, but I could be lying. Let's say that could be more. I'm not super sure if that is an accurate description of the global of the climate change. You need a big scale of time to actually see this. So you see variations. So 1 year could be really hot, 1 year could be, but that doesn't matter. It's the long-term trend which really makes the difference. So yes, so we are taking 8 years. I almost believe that those are going up, but this model will be blind to those things because we're just taking 5 days, predicting the next, and we are not taking anything of that in consideration. So that will be like a correction of the model. That will be a model that is taking, let's say, what all the temperatures or values from 1 year to try to predict what happens, that will happen tomorrow. And that is not what this model is doing. It's a short-term prediction. Okay, yeah, that's it. And also, these kind of networks can not only be used like to that, but also for classification. If something goes into different categories of, I saw one paper of people using this in the LHC, so the Large Hadron Collider in Switzerland, France, and so the large accelerator where they try to capture some signals with those neural networks. So those things are used in high energy physics. I know that, but yeah, I saw one paper related to that. So yes. Okay, thank you very much. Remember, you can ask for your accounts. I think those training accounts will stay for a few days, so you have time to gather those notebooks. There are a few things that I probably will do, if not today, tomorrow. I remember that I have one notebook where I put B_B with a subscript I, which is wrong. So I will be correcting a few typos or a few errors that I made on the equations in LaTeX at some point. and I was rushing writing, so my English should be horrible. That it should be even worse than when I speak. So I will try to correct some of those, so you get slightly better notebooks. And remember, fill those forms that Kyle is sending on the chat. So Daniel will put those, so you provide me some feedback. So yes, I can do that. I can send a message to the mailing list. So when I correct the things that I know for sure, there is one image in this. There is one image that doesn't work. Also works in my computer. No, it doesn't work here because I put it like a PDF. So I need to make a PNG version of this. This was my mistake. It works on Mac, but it doesn't work on. So I remember that. I remember a few questions that are wrong. Check those. By the way, I strongly recommend some of those books you can actually download here from the university. Just to tell you, for example, this book, you can download it legally with no problem. If you go to libraries, so this is something that could be interesting. Things like this. You search here deep learning. And there are some books that you can download. You can select here.
Is a deep learning.
Oh yeah, deep learning. Books. There is something that filter for books, source type, ebooks. So, for example, this one, I never pay attention to this one, but so this one, for example, is there. Sometimes you can download the entire book. So I will try to pick that one, for example, is the Scansi. Let me see if because I know that for sure that you can download it for the full text. So yes, this one. So you go here, let's say access now, online access. It will go to a Springer link. I think is here, and if you want the book, all you need to do is download the book in PDF, and you are actually downloading the entire book. So this is a nice thing. The university, I imagine that they pay a significant amount of money to make this available, and I don't know how many people actually knows that you can download many books in many areas of science, complete. In some other cases, for example, this book that I have here with me, this book, you can download a certain number of chapters, so you can see it on the web, but you cannot download it. So those from Springer, you can download those complete in the integral book. In some others, you have to read the books online. And so yeah, that could be something that it could be good. So many of those books that I put here, always in the reference, are books that are relatively easy. Some of those probably not, but some of those here, O'Reilly, they have it. The university have some subscription with the libraries for downloading those books for students, faculty. So that's something that it's good to know. So you can make this one. I strongly suggest. The problem with this kind of efforts is they become encyclopedic, so it will be hard to use them for teaching, because many people is contributing to those. If you try to print those, it's like 1,000 pages. But they have a lot of things. So if you want to see here, for example, what I mentioned here, the recurrent neural networks is right here. So the launch, this one that I was mentioning here, they will show about all those inputs becoming from. So they have all the equations, all the nice plots and examples in PyTorch, MXNet, and TensorFlow. So that's another thing. This is a good resource for those who want to learn this abstracted from a very particular implementation, a very particular framework. The book is nice. I suggest at least to read this introduction. I think this introduction is long. It's long, it's very verbose. So it's something that I can just suggest for reading, but I skip all that. So this is another good source for this. More mathematical books for those who are strong in statistics. Also, this one is a classic on that, Elements of the Statistical Learning. So it's old, but those mathematical books, they never really age. So those books here are in good order, from the easiest to the more mathematical, more demanding. So I more or less put them in that order. They are part of my collection, my personal collection of books of this area. And here the same. So from very introductory books like this one, No Equations, trying to be very informative for a, let's say, well-educated citizen. Those are really nice. And after you progress into books more pragmatic for like those for specific frameworks. And this one is the mathematical book. So with this book is, okay, you see the equations, but you don't know how to do it in practice with a specific, so you can be misled by that, but there is a big distance between what you learn from here from what you learn from this. So this one, so by the way, by the end of this month in August 30, if you go to Exceed, or I think here, if you want to learn this, a lot of the material they use was inspired from PSC. This is the Pittsburgh Supercomputer Center. So 1.5 hours from here, they have training, and in those training they have workshops. And here in August 30 and 31st, they have a workshop on big data and machine learning. For those who are interested, those workshops are really nice. I attend those, even if I attended like 5 times, because they have adding more materials and they are very illuminating for me when you want to teach a topic. It is really good. So you can register for those. It's free with something that was called Exceed. They changed name for something now they call Access, but you can register for those workshops. They offer workshops in HPC, in big data. They have another workshop for parallel programming, and they have another workshop for GPU programming, so OpenACC and CUDA. So yeah, so they have those MPI. This one for those who want to learn the guts of how you program GPUs. And this one, that is what I told you. So they have those. And I think in there, the slides are available. So you can go and see the slides. So you feel motivated to hear what they have to say about those topics. And they go into, well, it's an hour. It's like 2 or 3 hours dedicated to deep learning. So they are really, really fast in the presentation, but they also present things that I never talk about, like Habarocus, some other things for running massively. Are there some other resources? This is here. What else? What else? Again, these notebooks, this blog is good. If you feel interested in learning this, from a more general mathematical perspective, those are good. I really recommend those videos. Yeah, they're really good, very visual about what the neural network does. So check those. Are very well done. They explain the backpropagation, they explain the convolutions, all those things with even calculus. They have a section with calculus. They are really nice. So this is another perspective out of equations and things that I cannot do because I don't have the ability to put those animations here on Jupyter notebooks, or not so easily for me. So check those. Those are materials. Those I paste those on every single notebook there. So that's it. I hope you enjoyed. You learned something from me, and I'm very happy. Never I have this many number of people attending. Last year was Spark. Before that, it was more than Fortran. So with that, I scared people, and only 3 people appear. And I think at some point I was teaching to an empty room. So now it's different. So I'm very glad that that